Hello there, and welcome to Science for Sleep, a place where curiosity slows down, thoughts soften, and science takes the long, scenic route toward rest. Tonight, we're going to talk about something so large that even the word large starts to feel a little inadequate. Not loud, not urgent, just quietly overwhelming in the way the universe often is when you give it a moment to breathe. Somewhere far beyond our familiar sky, beyond the stars you might recognize, and the constellations you learned as a child, something enormous exists. Not enormous in the everyday sense, like a mountain or an ocean, but enormous in a way that challenges the limits of how our minds handle scale at all. A star so vast that for years astronomers argued about whether it could even be real. A star so extreme that it pressed uncomfortably against the rules we thought stars had to follow. And recently, thanks to a new eye on the universe, that argument shifted. That eye belongs to the James Webb Space Telescope, and what it has revealed is forcing scientists to recalibrate their sense of what is possible. Not dramatically, not with headlines screaming certainty, but slowly, carefully, through measurements, light, and patience. The kind of revelation that doesn't shout, but instead sits with you, growing heavier the longer you think about it. Before we go any further, take a second to notice where you are right now. Are you listening late at night, with the lights low and the day finally behind you? Or maybe it's early morning, the world's still quiet, not quite ready to start. Where are you listening from? And what time is it there, in your small, specific corner of a very large universe? If you find this gentle exploration calming, or if you enjoy drifting off while the cosmos slowly expands in the background, consider liking the video or subscribing. It helps this quiet little space reach others who might need a moment of calm too. No rush, no pressure, just an invitation. Now let's ease into the story. The universe has a strange habit of breaking our intuition. We're comfortable with sizes that fit into our lives. Rooms, streets, cities, even planets to some degree, because we can put numbers to them and pictures in our heads. Earth is about this big. The Sun is much bigger than Earth. The distance between them takes light 8 minutes to cross. These are facts we can memorize, repeat, and even explain. But understanding is something else. Understanding requires the brain to build a feeling, not just store a number. And when it comes to truly massive objects, the brain tends to protest. It starts simplifying, compressing, turning incomprehensible scales into something vaguely manageable. We say huge, gigantic, unfathomable, and hope that's enough. Most of the time that works, until something comes along that refuses to fit neatly into the boxes we've prepared for it. Stars, for example, already live at the edge of our imagination. Our sun is so large that you could fit more than 1 million Earths inside it, and yet, in cosmic terms, the sun is not especially impressive. It is stable, middle-aged, calm, a reliable engine quietly converting hydrogen into helium day after day for billions of years. But scattered across the universe are stars that make our sun look almost polite by comparison. Stars dozens, sometimes hundreds of times more massive. Stars that burn so intensely that they tear at themselves from the inside. Stars that live fast and die young, leaving behind black holes, neutron stars, or explosions so powerful they briefly outshine entire galaxies. For a long time, astronomers believed there was a practical ceiling to how massive a star could be, not because nature dislikes ambition, but because physics is stubborn. As a star grows, its gravity pulls more material inward. At the same time, the light produced by nuclear fusion pushes outward. At some point, the outward pressure should win. Add too much mass, and the star should simply blow its own outer layers away, unable to hold itself together. This balance is delicate. It is one of the quiet negotiations that happen constantly in the universe, far from our awareness, and for decades calculations suggested that stars much larger than a certain limit simply should not exist for long, if at all. Then came hints that maybe they did. At first, these hints were frustratingly unclear. A blur of light here, a spectrum that didn't quite match expectations there. Old telescopes could see parts of the story, but not all of it. Dust obscured key regions, distant softened details. The universe, it seemed, was keeping some of its secrets well hidden. That is where the James Webb Space Telescope changes the conversation. Unlike its predecessors, Webb sees primarily in infrared light. This allows it to peer through clouds of dust that block visible light, revealing regions of star formation that were previously concealed, places where stars are born in crowded, chaotic environments, places where gravity, radiation and time collide in complicated ways. When Webb turned its attention to certain massive stellar candidates, something unexpected happened. Measurements grew more precise, uncertainties narrowed, and the upper estimates for size and mass didn't shrink. They grew. One star in particular stood out, not because it was flashy or dramatic in appearance, but because of what the numbers quietly implied. Its luminosity, its inferred mass, the sheer amount of energy pouring out of it every second. Together, they suggested something that felt uncomfortable. This star, nicknamed Behemoth by astronomers, who perhaps needed a shorthand for their disbelief, appeared to sit well beyond what many models had predicted was possible. Now, it's important to pause here and soften the moment. Science does not work by sudden declarations. No one flipped a switch and announced that everything we know is wrong. Instead, this realization unfolded slowly. Researchers checked their assumptions. They recalculated distances. They asked whether the object might actually be multiple stars masquerading as one. They considered whether dust or lensing effects could be exaggerating the signal. Again and again the data held. The universe, it seemed, was gently insisting that something bigger was happening. To appreciate why this matters, we need to talk about scale in a more personal way. Not numerical scale, but mental scale. Your brain did not evolve to understand objects that are millions of times larger than your world. It evolved to judge distances across a field, the size of an animal, the reach of a tree branch. Even cities stretch our intuition. That's why maps feel comforting. They shrink reality into something we can hold. When scientists say that Behemoth may be tens or even hundreds of times the mass of the Sun, the brain nods politely and moves on. But that mass is not just a number. It represents an enormous concentration of matter, pressure, and energy, all confined within a volume that, while vast, is still fighting against its own internal violence. Imagine, not poetically but practically, the amount of fuel being burned. Every second, Behemoth converts unimaginable quantities of hydrogen into heavier elements. The energy released is so intense that it creates powerful stellar winds, streams of particles racing outward at millions of kilometers per hour. These winds carry mass away from the star, sculpting its surroundings, influencing nearby stars, and reshaping the environment in which it exists. And yet, despite losing material, the star remains enormous. Which raises a quiet but persistent question. How did it get that big in the first place? Star formation is not a tidy process. Stars form inside vast clouds of gas and dust, collapsing under gravity. Most of the time, the process fragments. One cloud becomes many stars, sharing the available material. But in rare environments, conditions align differently. Gravity dominates. Competition is fierce. One object grows faster, pulling in more material before its neighbours can claim it. Webb's observations suggest that Behemoth may have formed in such an extreme nursery, a place dense enough, massive enough, and turbulent enough to feed a star beyond what we once thought sustainable. This is where the phrase true scale begins to matter. Before Webb, astronomers could estimate sizes, but uncertainty was built into every calculation. Distance errors multiplied, dust blurred boundaries, light scattered and softened. Now, those uncertainties are shrinking, not disappearing, but tightening. And as they tighten, Behemoth does not become smaller. it becomes more confidently enormous. That confidence has consequences, because stars like Behemoth do not exist in isolation. Their mass influences how long they live, how they die, and what they leave behind. Extremely massive stars are prime candidates for forming black holes far larger than typical stellar remnants. Some may collapse directly, without a visible supernova. Others may explode so violently that they seed entire regions of space with heavy elements. Those elements, in turn, become the building blocks for planets, atmospheres, and eventually life. Carbon, oxygen, iron, all forged in stellar cores or explosive deaths. So when we talk about the scale of Behemoth, we are not indulging in cosmic trivia. We are touching the upstream source of much of what makes complex structures possible in the universe. Still, there is something subtly unsettling about objects that push past theoretical limits. Physics relies on boundaries. They help us predict behavior. When something appears to cross those boundaries, we have to ask whether the boundary was wrong, incomplete, or misunderstood. In this case, the answer may be all three. The models that predict upper limits for star size depend on assumptions about stability, symmetry, and time. But real stars are messy. They rotate, they pulsate, they shed mass unevenly. They interact with nearby stars, and over short periods they may exist in unstable states that are rare, brief, but real. Webb may be catching Behemoth in such a phase, a moment in its life when it is temporarily defying expectations, burning furiously, shining outrageously, before gravity and radiation finally settle their argument. That possibility alone is enough to reshape how astronomers think about stellar evolution at the highest masses. As we sit with this idea, it helps to remember something grounding. The universe is not obligated to make sense to us immediately. It does not scale itself politely to fit our theories. It reveals itself gradually, often through instruments that extend our senses beyond their natural limits. The James Webb Space Telescope is one such extension. Not a replacement for curiosity, but an amplifier. It takes faint, stretched light that has travelled for millions of years and turns it into information we can analyse. It allows us to see not just farther but more clearly through the clutter that once obscured key details, and with that clarity comes humility. Because every time we think we've bracketed reality into neat categories, something like Behemoth reminds us that the universe still has room to surprise us, quietly, persistently, without asking permission. As this story continues, we will move slowly outward. We will talk about how astronomers measure stars that cannot be visited, how mass is inferred from light, why brightness alone can be misleading, and how scale, once it passes a certain point, stops behaving the way our intuition expects. For now, just let the idea settle. Somewhere out there, a star exists whose size presses against the edges of what we believed possible. Not as a challenge, but as a fact revealed not all at once, but piece by piece, as our tools improve and our patience deepens. Before we go any farther into measurements, instruments, or distant stars, it helps to pause on a deceptively simple question. What do we actually mean when we say that something is big? Not rhetorically, not emotionally, but in the practical sense of how the human mind understands size at all. Because big is not a fixed idea. It stretches and shrinks depending on context. A big dog feels enormous to a child and fairly ordinary to a zookeeper. A big city can feel endless when you're lost in it, and surprisingly small once you learn its streets. Size is always relative, always anchored to something familiar. This becomes a problem when the familiar runs out. Our brains evolved to judge scale within a narrow window. The width of a river, the height of a tree, the distance to the horizon. Even when we talk about mountains or oceans, we're still operating within a range that can be experienced directly, or at least imagined by stitching together memories of smaller things. Astronomical size does not play by those rules. When scientists talk about stars that are dozens or hundreds of times more massive than the Sun, the numbers alone do very little. The brain hears them politely, then quietly replaces them with something vague and manageable. Very large. Extremely massive. Labels that feel informative but do not carry weight. That weight is what we need to understand. Consider the sun for a moment, not as a symbol, but as an object. Its diameter is about 1.4 million kilometers. Light, which moves faster than anything else we know, takes more than 4 seconds to cross from one side of the sun to the other. The sun's mass accounts for more than 99% of everything in the solar system. Planets, moons, asteroids, comets, altogether barely register by comparison. Already this stretches intuition, and yet the sun is considered a modest star. Now imagine a star with 50 times that mass, or 100 times. The increase is not gentle. Gravity does not scale linearly. Pressure rises dramatically. Temperatures climb. Nuclear reactions accelerate. Every additional unit of mass intensifies the internal struggle between collapse and explosion. This is where size stops being just about volume and starts becoming about behavior. Big things behave differently. On Earth, we see this all the time. A drop of water forms a bead, a puddle spreads, an ocean follows gravity and rotation into currents and tides. The same substance, entirely different behavior, simply because scale changes which forces dominate. Stars are no different. Small stars can exist calmly for trillions of years, sipping fuel at a leisurely pace. Larger stars burn brighter and faster, their lives measured in millions of years instead. At extreme sizes, stars become unstable by default. Their radiation pushes outwards so forcefully that it threatens to tear them apart. For decades, astrophysics textbooks included a comfortable assumption. There is an upper limit, a point beyond which stars cannot grow, because the physics that holds them together would fail. That assumption did not come from guesswork. It came from equations, simulations, and observations that seem to agree. Above a certain mass, radiation pressure should overpower gravity. Material trying to fall inward would be blown away before it could settle. The star would starve itself, unable to grow further. In theory, this limit made sense. In practice, the universe appears to be less tidy. When astronomers first began encountering candidates for ultra-massive stars, skepticism was immediate and healthy. Distance measurements are tricky. Brightness can be misleading. 2 stars close together can masquerade as one. Dust can amplify or distort signals. Every possible source of error had to be considered. That skepticism is still there, but it is now paired with something else. Data. One of the challenges in grasping just how large Behemoth appears to be is that size in astronomy is rarely measured directly. No one stretches a cosmic measuring tape across a star. Instead, scientists infer size from light, motion, and models that connect the two. Brightness plays a key role. A star's luminosity tells us how much energy it is releasing. Combine that with temperature, and you can estimate surface area. Combine that with gravity, and you can infer mass. Each step depends on assumptions, but when multiple independent methods point in the same direction, confidence grows. What Webb has done is reduce the fog around those steps. By observing in infrared wavelengths, it sees through dust that previously hid critical regions. It resolves structures that were once blurred. It sharpens spectral lines that reveal temperature, composition, and motion. Each improvement trims uncertainty. And as those uncertainties shrink, Behemoth remains stubbornly, uncomfortably large. This is where the word scale becomes more than a measurement. It becomes a cognitive challenge. The human mind handles scale by comparison. We understand a kilometre because we can walk it. We understand 1,000 kilometres because we can imagine driving across a country. But once distances exceed Earth entirely, the scaffolding collapses. Astronomers often try to help by stacking comparisons. The Sun compared to Earth. Behemoth compared to the Sun. Galaxies compared to stars. Each rung helps, but only briefly. Eventually the ladder becomes too tall. At that point, something interesting happens. Instead of visualizing, the brain shifts into abstraction. Size becomes symbolic rather than spatial. We stop imagining the object itself and start imagining what it does. That is not a failure. It is a survival strategy. So rather than asking what Behemoth looks like, it may be more useful to ask what its size allows it to do. Its gravity dominates its surroundings. Nearby gas clouds are shaped by its presence. Its radiation sculpts stellar nurseries, compressing some regions while eroding others. Its lifespan is short but intense. Every moment of its existence is energetic, disruptive, and consequential. In that sense, Behemoth is less like a static object and more like a process, a temporary but powerful phase in the life of matter. This reframing helps with another subtle issue. When we say a star is huge, we often imagine something peaceful and majestic, like a larger version of the sun hanging serenely in space. But extreme size does not come with serenity. It comes with violence, even if that violence unfolds quietly over millions of years. Inside Behemoth, pressure and temperature reach levels that push atomic nuclei together with relentless force. Fusion reactions race. Energy floods outward. The star sheds mass through stellar winds that are not gentle breezes, but torrents of particles escaping at extraordinary speeds. Paradoxically, this loss of material is part of what allows the star to exist at all. Without shedding mass, it might collapse or explode prematurely. Stability at this scale is dynamic, not static. Understanding this helps resolve some of the discomfort around size limits. The universe may allow stars to exceed traditional boundaries, but only temporarily, only under specific conditions, and only by constantly bleeding energy and matter into their surroundings. In other words, too big may not mean impossible, it may mean unstable. There is another layer to scale that often goes unnoticed. Time. Large stars live fast. Their internal clocks run quickly. The same processes that take billions of years in smaller stars unfold rapidly in giants. A massive star might burn through its nuclear fuel in a few million years, a blink on cosmic timescales. So when we encounter something like Behemoth, we may be witnessing a rare moment, a short-lived configuration that does not last long enough to be common. Its apparent defiance of limits may simply reflect that we are catching it mid-breath, before physics reasserts itself in a more familiar form. This matters because rarity affects perception. If something is rare enough, it can feel like an anomaly even when it is a natural outcome of known laws playing out under extreme conditions. The universe is large enough to explore its own edge cases. There is also a psychological aspect to size that deserves attention. Humans tend to associate largeness with importance. Big events feel more meaningful. Big structures feel more significant. But the universe does not share this bias. Tiny particles shape reality just as profoundly as massive stars. Small changes can have enormous consequences. Behemoth's significance does not come from its size alone. It comes from what that size reveals about the rules governing matter, energy, and formation. It tells us that under the right conditions, nature can assemble structures that flirt with instability and still persist. At least for a while. That insight ripples outward. It affects how we think about early galaxies, where conditions were denser and more chaotic. It influences models of black hole formation, especially the question of how supermassive black holes appeared so early in cosmic history. It reshapes expectations for what kinds of stellar populations may exist in extreme environments. In all of this, big stops being a simple descriptor and becomes a diagnostic tool. The question shifts from how large is it to what does its largeness make possible? As we sit with this, it is worth returning briefly to your own scale, the room you're in, the device you're listening on, the steady rhythm of breath and heartbeat. These are not insignificant, they are simply tuned to a different range. One of the quiet comforts of astronomy is that it allows us to hold multiple scales at once, the intimate and the immense, the immediate and the distant. Neither cancels the other out. Behemoth does not make you smaller, it simply expands the context. That story builds naturally from here, because once size stretches intuition, the next question becomes unavoidable. How do we know what we think we know at all? Long before the James Webb Space Telescope ever unfolded its mirrors in space, astronomers were already wrestling with the question of how large stars could truly become. Not casually, not speculatively, but through decades of observation, calculation, and careful restraint. What we thought we knew was not ignorance. It was a structured understanding built from the best tools available at the time. To appreciate why Webb's revelations matter, it helps to sit with that earlier picture for a while, not to dismiss it, but to understand its limits. For most of the 20th century, our view of stars was shaped by visible light. Telescopes collected photons our eyes could, in principle, detect. This worked remarkably well for nearby stars and relatively clean regions of space. Stellar classification flourished. Spectral types were refined. The life cycles of stars were mapped with increasing confidence. Massive stars were already known to be rare and extreme. Observation showed that stars much larger than the Sun existed, burned hotter, lived shorter lives, and ended violently. But even then, there seemed to be a ceiling. Around 100 to 150 times the mass of the Sun appeared to be the upper bound. Beyond that, stars were expected to be unstable, unable to hold themselves together. This expectation came from physics that was, and still is, sound. As stars grow more massive, their cores become hotter and denser. Fusion reactions accelerate. The energy released does not simply vanish. It pushes outward as radiation pressure. At some point, that pressure becomes strong enough to counteract gravity's inward pull, add more mass, and the push should exceed the pull. In that framework, stars above a certain mass should shed material rapidly, preventing further growth. This concept, often referred to as the Eddington limit, became a cornerstone of stellar astrophysics. It was not a guess. It was a balance derived from fundamental forces. Observations seemed to agree. The most massive stars identified clustered near that theoretical boundary. A few outliers appeared now and then, but they were usually explained away. Distance uncertainties, binary systems masquerading as single stars, dust amplification, measurement error. And in many cases, those explanations were correct. The universe is not always cooperative when it comes to clean data. Stars form in crowded regions. Light travels immense distances, losing clarity along the way. Dust absorbs and re-emits radiation. Even determining how far away an object is can involve layers of inference stacked on top of one another. Before Webb, astronomers relied heavily on telescopes like the Hubble Space Telescope, which transformed our understanding of the cosmos in profound ways. Hubble gave us sharp images, deep fields, and a clearer picture of stellar populations in other galaxies. It extended our reach and refined our models, but Hubble had limitations, especially when it came to the environments where the most massive stars are born. Those stars tend to form in dense, dusty regions, clouds of gas and dust that glow faintly in visible light but shine brightly in infrared. Hubble could see the edges of these regions, but not always their cores. The brightest stars were often partially obscured, their light reddened or scattered, their true output difficult to measure accurately. As a result, estimates of stellar mass relied on indirect methods. Luminosity had to be corrected for dust extinction. Temperature had to be inferred from spectral features that might themselves be altered by surrounding material. Models had to assume symmetry and stability that might not exist in reality. This did not make the science weak, it made it cautious. Astronomers learned to trust patterns rather than outliers. A single, extraordinarily bright star might be interesting, but unless it fit into a broader population, it remained suspect. Claims of ultra-massive stars were met with skepticism not out of stubbornness, but out of discipline. The history of astronomy is filled with cases where initial excitement faded under closer scrutiny. Objects once thought to be exotic turned out to be mundane. apparent anomalies resolved into measurement artifacts. Caution became a survival skill, so when early hints of stars pushing beyond accepted mass limits appeared, they were treated carefully. Researchers asked hard questions. Could the object actually be multiple stars unresolved by the telescope? Could the distance be overestimated? Could dust be artificially boosting the apparent brightness? Often, the answer was yes. In some cases, stars once thought to be impossibly large were later resolved into clusters. In others, improved distance measurements brought their estimated mass back into comfortable territory. Each correction reinforced the idea that the theoretical ceiling held. By the early 2000s, a kind of consensus settled in. Extremely massive stars existed, but they were bounded. The universe might flirt with the edge of that boundary, but it did not seem to cross it. That consensus shaped how astronomers interpreted new data. Models of stellar formation assumed that radiation pressure would halt accretion beyond a certain point. Simulations reflected that assumption. Population studies built it in as a constraint. Even when massive stars were detected in young star clusters, their inferred masses clustered near the expected maximum. The picture felt coherent, and coherence is comforting. Yet there were cracks, subtle and easy to overlook. Some star-forming regions appeared to produce stars that were brighter than models predicted. Some clusters showed signs of extreme feedback, as if something unusually powerful was shaping the surrounding gas. These hints did not overthrow the consensus, but they unsettled it slightly. Still, without clearer data, there was little reason to rewrite the rules. This is an important moment to pause because it highlights something essential about science. Knowledge is not static, but neither is it reckless. It advances by refining what we already think we know, not by discarding it impulsively. Before Webb, astronomers were not wrong. They were working within the constraints of their instruments. Another limitation worth mentioning is time. Massive stars evolve quickly. Their most extreme phases may be brief. Catching one at just the right moment requires both luck and reach. If a star spends only a small fraction of its life at its most massive and luminous, the odds of observing it during that phase are low. Add distance and dust, and the challenge multiplies. In this context, Behemoth, or stars like it, could have existed unnoticed for a long time, not because astronomers were careless, but because the universe did not make them easy to see. There is also the issue of interpretation bias. When data is noisy, scientists tend to favour explanations that fit existing frameworks. This is not a flaw. It is a way to avoid overfitting noise. Extraordinary claims require extraordinary evidence, and for a long time, that evidence was simply not strong enough. So what we thought we knew was grounded in reasonable physics, supported by the best observations available and reinforced by repeated confirmation. The idea of an upper mass limit for stars felt secure. What Webb has done is not to invalidate that framework outright, but to expose its edges. By observing in infrared, Webb peers directly into star-forming regions that were previously opaque. It sees stars earlier in their lives, before winds and radiation have stripped them down. It measures luminosity with fewer corrections. It resolves structures that once blurred together. This clarity matters because it reduces the wiggle room for comfortable explanations. When Webb observes a luminous object deeply embedded in a stellar nursery and sees signatures consistent with a single, extraordinarily massive star, the usual escape routes narrow. Distance estimates improve. Dust effects are constrained. Multiplicity becomes easier to rule out. Suddenly, what once felt like an outlier begins to feel persistent, and persistence is what shifts understanding. Before Webb, the story of massive stars was one of boundaries and balance. After Webb, the story appears more dynamic. Limits still exist, but they may be higher, fuzzier, or more context-dependent than we thought. The universe may allow stars to exceed traditional mass ceilings under certain conditions, even if only briefly. It may tolerate instability longer than expected, or it may offer formation pathways that bypass some of the constraints we assumed were universal. None of this makes earlier work obsolete. Instead, it reframes it as part of a longer narrative. The models built before Webb were tuned to the stars we could see clearly. Now we're seeing a different population, one that lived mostly hidden, shaping its environment in ways we're only beginning to understand. As we move forward, the question becomes less about whether past astronomers were mistaken, and more about how the universe behaves when pushed to extremes we're only now able to observe. Once assumptions are challenged, methods come under scrutiny. How exactly do astronomers measure stars at such distances? How reliable are those measurements? And what does it mean when independent techniques converge on unsettling answers? High above Earth, far beyond the reach of weather, cities, and the faint glow of our atmosphere, a mirror unfolds in silence. Not dramatically, not with sound or spectacle, just slowly, precisely, piece by piece, until it forms something that did not exist before, a new way of seeing. The James Webb Space Telescope does not orbit Earth the way the Hubble Space Telescope does. It lives much farther out, near a region known as the second Lagrange point, about 1.5 million kilometers away. From there, it maintains a delicate gravitational balance with Earth and the Sun, moving with us as we orbit, always facing outward into deep space. That distance matters. Earth is warm. It glows in infrared light. Even our own atmosphere radiates heat that can interfere with sensitive instruments. Webb was designed to avoid that interference entirely. It carries a massive sunshield, layered and reflective, always positioned between its mirrors and the sun. One side of the telescope basks in sunlight. The other remains in deep cold, chilled to temperatures where even faint infrared signals from distant stars can be detected. This is not just an engineering achievement, it is a philosophical one. For centuries, astronomy relied on visible light, the same light our eyes evolved to see. But the universe does not emit only what we find convenient. Some of its most important stories are told in wavelengths our eyes cannot detect. Infrared light, in particular, carries information about cooler objects, dust-shrouded regions, and the early universe itself. Dust is one of astronomy's most persistent obstacles. Vast clouds of microscopic particles drift between stars, absorbing and scattering visible light. To earlier telescopes, these regions appeared dark, opaque, almost empty. But in infrared, that same dust becomes partially transparent. Light that was blocked in visible wavelengths passes through more easily. Imagine trying to look through thick fog with ordinary sight. Everything blurs, shapes disappear. Now imagine switching to a different kind of vision that can see through that fog, revealing what was always there but hidden. That is what Webb does. Its primary mirror spans about 6.5 meters in diameter, composed of 18 hexagonal segments, coated in a thin layer of gold. Not decorative gold, but functional. Gold reflects infrared light extremely well. Each segment can be adjusted with extraordinary precision, aligning to form a single, coherent surface. When light from a distant object reaches Webb, it has often travelled for millions, sometimes billions of years. The photons that strike its mirror began their journey long before human civilization existed. Webb collects them, focuses them, and directs them into instruments designed to separate and analyse their wavelengths. That analysis reveals temperature, composition, motion, and more. In the case of Behemoth, or stars like it, this capability changes everything. Massive stars form in dense stellar nurseries, places thick with gas and dust. In visible light, these nurseries appear as dark patches or faint glows. Earlier telescopes could detect the brightest stars emerging from the edges, but the cores of these regions remained obscured. Webb looks directly into those cores. Instead of guessing how much light is being hidden by dust, astronomers can measure it more directly. Instead of relying on heavily corrected brightness estimates, they can observe emission lines that cut through the clutter. Instead of seeing a blur, they see structure. This clarity sharpens the numbers. Stellar mass is not measured by placing a star on a scale. It is inferred through models that connect luminosity, temperature, and spectral features. If brightness is underestimated because dust blocks some of the light, then mass estimates will also be low. If multiple stars blend together in a single fuzzy point of light, mass estimates might be artificially high. Webb reduces both of these uncertainties. When its instruments observe a luminous object deeply embedded in a star-forming region and resolve it into a single source, the case strengthens. When the spectrum reveals temperatures and ionization states consistent with an extremely massive star, confidence increases further. This is how Behemoth begins to solidify from possibility into evidence. Another advantage Webb brings is sensitivity. It can detect extremely faint infrared signals. That matters because massive stars, while luminous, may still be partially veiled by surrounding material. Earlier telescopes might have missed key details, especially in distant galaxies where resolution is stretched thin. With Webb, distance becomes less of a barrier. It is important to understand that Webb does not invent new stars. It reveals them more clearly. The objects were always there. The difference is resolution, wavelength, and sensitivity. Before Webb, astronomers often had to rely on composite data sets. Visible light from one telescope, radio observations from another, X-ray data from yet another instrument. Each wavelength offered a partial view. Together they formed a mosaic, but gaps remained. Webb fills some of those gaps. When studying something as extreme as Behemoth, small differences matter. A slight change in temperature estimate can shift mass calculation significantly. A clearer separation between two close stars can halve an earlier estimate. Precision accumulates, and precision, when applied consistently, reshapes boundaries. Webb's infrared spectrographs are particularly powerful tools. They disperse incoming light into detailed spectra, allowing astronomers to identify specific atomic transitions. These transitions act like fingerprints, revealing which elements are present and how they are behaving. In massive stars, certain spectral lines become extraordinarily strong due to high temperatures and intense radiation fields. By analysing these lines, researchers can constrain the star's surface gravity and luminosity. Combined with models of stellar structure, these constraints lead to revised mass estimates. What makes this moment remarkable is not that Webb discovered something entirely alien to physics. It is that it tightened the constraints so much that the old comfort zones shrank. Behemoth's inferred mass did not collapse under scrutiny. It held. There is also the matter of context. Webb does not observe stars in isolation. It captures entire star-forming regions in stunning detail. Clusters of young stars, filaments of gas, shock fronts from stellar winds, all visible simultaneously. This broader view helps astronomers understand the environment that allowed such a massive star to form. If Behemoth exists within an exceptionally dense cluster, where gravitational interactions and gas inflows are intense, then formation pathways previously considered unlikely become more plausible. In other words, Webb does not simply measure size, it reveals conditions, and conditions matter. Massive stars require enormous reservoirs of gas. They require time, but not too much time, because radiation pressure quickly begins to push material away. The balance between accretion and feedback is delicate. Seeing the surrounding gas flows directly helps astronomers test whether their formation models hold up under real-world conditions. Another subtle advantage of Webb lies in its stability. Operating far from Earth, shielded from thermal fluctuations and atmospheric interference, it maintains a remarkably steady observational platform. That steadiness improves signal-to-noise ratios, allowing fainter features to be extracted from data. For Behemoth, that means spectral lines can be measured with greater confidence. Variability can be tracked over time. Stellar winds can be characterized more precisely. All of this accumulates into something that feels simple on the surface. The star appears extremely massive, But beneath that simplicity lies a chain of engineering, mathematics, and patience stretching back decades. It is worth reflecting briefly on how long it took to reach this point. Webb was proposed in the 1990s. It faced delays, budget overruns, technical challenges, and skepticism. Building a telescope that unfolds in space, aligns itself with nanometer precision, and operates at cryogenic temperatures is not trivial. And yet, here it is. The mirror in deep space is not just a tool. It is a reminder that extending human perception requires effort measured in decades. The questions we can answer depend on the instruments we are willing to build. Behemoth, in a sense, is a reward for that patience. As Webb continues to observe, it may find even larger candidates, or it may refine current estimates downwards slightly. Science remains open to correction, but the crucial shift has already happened. The observational floor has dropped away. The hidden regions of star formation are no longer entirely hidden. We're now looking directly into the furnaces where the most massive stars ignite. And that changes the conversation. Before Webb, the upper limits of stellar mass were supported by theory and constrained by incomplete observation. With Webb, observation grows sharper, theory must adapt, and objects like Behemoth demand more nuanced explanations. How do astronomers translate infrared photons into mass values that challenge textbooks? What assumptions remain? Where could errors still hide? At first, it did not look like a revolution. It looked like data. A cluster of young stars deeply embedded in a dense stellar nursery, filaments of gas curling through space, bright points scattered across a field that, in earlier images, had seemed far less detailed. When the James Webb Space Telescope sent back its initial infrared observations of this region, astronomers did what they always do. They calibrated, they corrected, they compared. There was no dramatic announcement on the first day, no immediate declaration that something unprecedented had been found. Instead, there was a quiet pattern emerging inside the data. One object in particular stood out, not because it flared or pulsed, but because its brightness, once properly measured, did not sit comfortably within established expectations. The first glimpse of Behemoth was not visual in the way you might imagine. It was not about seeing an enormous disk hanging in space. At such distances, even Webb does not resolve the surfaces of individual stars beyond our immediate galactic neighbourhood. Behemoth appeared as a point of light, intensely luminous, embedded in its natal environment. What made that point different was the combination of brightness and spectral signature. Brightness alone is deceptive. A star can appear bright because it is intrinsically powerful, or because it is relatively close, or because multiple stars are overlapping in a tight cluster. The first step was to untangle those possibilities. Distance estimates were refined using surrounding stellar populations and known properties of the host region. Webb's infrared sensitivity allowed astronomers to see more clearly through dust that had previously muddied measurements. With better distance constraints, luminosity calculations became more reliable. The number that emerged was high, uncomfortably high. Still, luminosity does not directly equal mass. It correlates strongly for main sequence stars, but at extreme scales the relationship becomes steeper and more sensitive to internal physics. To move from brightness to mass, researchers needed more than photometric data. They needed spectra. Webb spectrographs dispersed the star's light into detailed wavelength bands. Within those bands, specific absorption and emission lines revealed the temperature of the star's outer layers. Certain ionized elements appeared prominently, indicating extraordinarily high surface temperatures. The radiation field required to produce those ionization states implied immense energy output. When temperature and luminosity were combined within established stellar models, the inferred mass began to climb. That was the first moment of tension. Astronomers are cautious by necessity. When a calculation yields a value that presses against or exceeds known limits, the immediate assumption is not that the universe has broken the rules. The assumption is that something in the measurement needs re-examination, so they re-examined it. Could the object actually be a tight binary system? Two or more massive stars so close together that they appear as one. Webb's resolution is powerful, but at extreme distances, even it has limits. Careful analysis of the point spread function was performed to look for elongation or asymmetry. None appeared beyond what instrumental effects could explain. Could dust be enhancing the infrared emission in a misleading way? Dust absorbs shorter wavelengths and re-emits in infrared, potentially boosting apparent brightness. But the spectral energy distribution did not match a dust-dominated source. The continuum and line features pointed clearly toward a stellar origin. Could variability be skewing the snapshot? Massive stars can fluctuate. Multiple observations over time were compared. While minor variations existed, the overall luminosity remained consistent with an extraordinarily powerful star. Each possible escape route narrowed. It is important to remember that Behemoth did not announce itself as impossible. It announced itself as persistent. The data refused to collapse into a safer interpretation. When astronomers speak of a first glimpse, they often mean the moment when suspicion becomes curiosity. Not certainty, but enough coherence to justify deeper investigation. That moment arrived quietly. Inside the research teams analysing Webb's early data, discussions sharpened, stellar models were revisited, parameters were adjusted, simulations were run with input values that, until recently, would have been dismissed as unrealistic. What happened next was subtle but significant. The models did not immediately fail. Instead, they showed that under certain extreme conditions, stars of such mass could exist, at least temporarily. The upper mass limit was not a hard wall, it was a region of instability. A star could inhabit that region, shedding mass rapidly, balancing on the edge of equilibrium, but still remaining intact for a measurable span of time. Behemoth appeared to be occupying that edge. Its stellar winds, inferred from broadened spectral lines, were powerful. Material was streaming away at enormous velocities. This was not a calm object. It was actively losing mass, perhaps at rates far exceeding smaller stars. And yet, despite this outflow, its core fusion processes continued, generating staggering energy. The first glimpse, then, was not of a stable giant in serene isolation. It was of a star in dynamic tension, holding itself together through a balance that seemed almost temporary. That realization altered the emotional tone within the scientific community. Before Webb, ultra-massive stars were often treated as statistical upper bounds. Rare, perhaps even questionable. After Webb's early observations, they began to feel more tangible, less hypothetical, more like natural, if uncommon, products of extreme star-forming environments. There was another factor in that first glimpse that deserves attention: context. Webb's wide-field infrared imaging did not isolate Behemoth against empty space. It revealed the surrounding cluster in extraordinary detail. Nearby stars of varying masses were visible. Gas flows and shock fronts from stellar winds traced the interactions between massive stars and their environment. This context reinforced the interpretation. Behemoth was not a solitary anomaly. It was embedded in a region capable of producing high-mass stars. The surrounding conditions supported the idea that sufficient material had been available during its formation. Star formation is competitive. In dense clusters, protostars compete for gas. Some gain mass more quickly than others, dominating their local environment. If Behemoth formed in an especially dense pocket, its growth may have accelerated before radiation pressure could halt accretion entirely. Seeing the environment made that scenario plausible. As the data circulated, independent groups began their own analysis. This is how science strengthens claims. Separate teams, using the same publicly available observations, test whether they arrive at similar conclusions. In the case of Behemoth, early independent assessments did not contradict the original interpretation. If anything, they reinforced it. That reinforcement did not eliminate uncertainty. It narrowed it. the mass estimate remains sensitive to assumptions about metallicity, rotation rate, and internal mixing. Massive stars often rotate rapidly, which can alter their internal structure and extend certain phases of their evolution. Adjusting these parameters shifted the mass estimate slightly, but not enough to bring it comfortably below traditional ceilings. This is the point where the phrase true scale begins to feel earned. Before Webb, the scale of such stars was blurred by dust and distance. Now the blur is thinner, the margins are tighter. Behemoth's inferred mass does not depend on a single fragile assumption. It rests on a network of observations converging. The first glimpse, therefore, was less about shock and more about recalibration. Astronomers did not gasp and rewrite textbooks overnight. They leaned in. They asked whether their understanding of upper mass limits needed refinement. They considered whether certain formation channels had been underestimated. It is possible that Behemoth represents the high end of a distribution that was always there, simply undersampled. It is also possible that Webb is catching a brief evolutionary stage that earlier instruments were statistically unlikely to observe. Either way, the existence of such an object pushes theoretical work forward. As the initial excitement settled into steady investigation, attention shifted toward what Behemoth's eventual fate might be. Extremely massive stars do not fade quietly. They collapse or explode, often leaving behind black holes that concede further cosmic structures. If Behemoth collapses directly into a black hole without a supernova, it could contribute to explaining how massive black holes form so quickly in young galaxies. If it explodes in an unusually energetic supernova, it could disperse heavy elements across vast regions. The first glimpse, then, was not only about present size, it was about future consequence. Yet even with all of this, it is worth grounding the moment in simplicity. A point of light, a spectrum, a set of numbers that refuse to shrink under scrutiny. That is how revolutions in astronomy often begin. Not with spectacle, but with stubborn data. As Webb continues to observe, additional candidates for ultramassive stars may emerge, or some current estimates may be refined downwards slightly as more data accumulates. The process remains ongoing. There is no final word yet. What remains clear is that the first clear look at Behemoth did not dissolve under pressure, it solidified. At some point, wonder gives way to method. After the first glimpse settles into cautious confidence, the next question becomes unavoidable. How do you measure something you cannot touch, cannot visit, and cannot even see as a surface? How do you turn faint photons, stretched by distance and dust, into numbers that claim to describe mass, size, and power on a scale that strains belief? This is where astronomy becomes less romantic and more meticulous, not cold, but careful. Measuring the unmeasurable is not a single act. It is a layered process built from inference, cross-checking, and an ongoing awareness of uncertainty. To begin, it helps to accept a simple truth. Astronomers do not measure stars directly. They never have. Even the closest stars remain unreachable in any physical sense. Everything we know about them comes from light and the way that light behaves. Light is generous, but it is not straightforward. When a star emits light, that light carries information about temperature, motion, composition, and energy output. By the time it reaches a telescope, however, it has been altered. It may have passed through dust, gas, magnetic fields, and gravitational distortions. Each interaction leaves a subtle mark. Extracting meaning from those marks is the heart of astrophysical measurement. The first quantity astronomers usually estimate is luminosity, the total amount of energy a star emits per second. This is not the same as brightness. Brightness is how much light reaches us. Luminosity is how much light leaves the star. The difference matters enormously. A star can appear dim because it is far away, even if it is incredibly powerful. Conversely, a nearby but modest star can appear bright. To move from brightness to luminosity, distance must be known with reasonable accuracy. Distance, in astronomy, is itself an inferred quantity. For nearby stars, parallax can be used, measuring the apparent shift in position as Earth orbits the Sun. For distant stars embedded in clusters or other galaxies, astronomers rely on standard candles, population models, and the known properties of surrounding objects. Before infrared observations improved, dust made these estimates harder. Dust dims and reddens starlight, making stars appear cooler and less luminous than they truly are. Correcting for this requires assumptions about the amount and distribution of dust, assumptions that introduce uncertainty. Infrared observations reduce but do not eliminate this problem. Infrared light penetrates dust more effectively, allowing astronomers to see closer to the star's true output. This is one of the reasons recent measurements feel more confident. Once luminosity is estimated, temperature enters the picture. A star's temperature is inferred from its spectrum, the pattern of light spread across different wavelengths. Certain elements absorb or emit light at specific wavelengths depending on temperature and pressure. By identifying these spectral lines and their strengths, astronomers can estimate the temperature of the star's outer layers. For massive stars, this step is particularly important. Their temperatures are extreme. Many emit most of their energy in ultraviolet or infrared, rather than visible light. If observations miss those wavelengths, estimates can be skewed. Combining luminosity and temperature allows astronomers to estimate the star's radius. This comes from a well-tested physical relationship. Hotter objects emit more energy per unit surface area. If you know how hot a star is and how much energy it emits overall, you can infer how large its surface must be. Radius, however, is not mass. To estimate mass, astronomers rely on models of stellar structure and evolution. These models describe how stars of different masses behave, how pressure, temperature, and fusion balance inside them, and how that balance changes over time. For many stars, mass can be measured directly if they are part of a binary system. By observing their orbital motion, astronomers can apply Newton's laws and determine mass with high precision. Unfortunately, the most massive stars are often not in clean, easily measured binaries, or they exist in crowded environments where orbital motion is difficult to disentangle. In such cases, mass must be inferred indirectly. This inference relies on comparing observed properties, luminosity, temperature, spectral features, to theoretical models. For ordinary stars, this works well. The relationship between mass and luminosity is relatively tight. For very massive stars, that relationship becomes more complex. Massive stars experience strong internal mixing, rapid rotation, and intense mass loss through stellar winds. These effects alter how energy moves inside the star and how it appears from the outside. Small changes in assumptions about these processes can shift mass estimates significantly. This is why claims about extreme stellar masses are approached cautiously. The uncertainty bars are wider, the models are sensitive. What changed with recent observations is not that these uncertainties vanished, but that multiple independent indicators began pointing in the same direction. Luminosity suggested extreme mass. Temperature supported that luminosity. Spectral signatures indicated strong winds consistent with very high radiation pressure. The surrounding environment appeared capable of feeding such a star during formation. Each piece alone might be questioned. Together they reinforce one another. Another important measurement involves surface gravity. This can be inferred from the widths and shapes of certain spectral lines. Strong gravity compresses a star's atmosphere, affecting how atoms absorb and emit light. By modelling these effects, astronomers can estimate how strong gravity is at the star's surface. Surface gravity depends on both mass and radius. If radius is known from luminosity and temperature, gravity measurements provide an independent check on mass estimates. For Behemoth, these checks do not collapse into a smaller value. They remain consistent with an unusually high mass. Still, there are caveats. Rotation, for instance, complicates everything. Rapidly rotating stars are not perfect spheres. They bulge at the equator and flatten at the poles. Temperature varies across their surface. Spectral lines broaden due to rotational motion. Interpreting these effects requires careful modelling. Massive stars also lose mass at prodigious rates. The mass inferred today may not reflect the mass the star had when it formed. In fact, it almost certainly does not. This means that when astronomers talk about Behemoth's mass, they are often referring to its current mass, not its peak mass. That distinction matters. A star could have formed with a mass well above current estimates, and already shed a significant fraction of it. If so, the true extremes of star formation may be even more dramatic than current numbers suggest. There is also the issue of timescale. Observations capture stars at a particular moment. Models describe average behaviour over time. When a star is observed during a brief, unstable phase, it may appear more luminous or massive than it would over most of its life. Accounting for this requires population studies. Astronomers look at entire clusters, counting stars of different types, and comparing those distributions to models. If objects like Behemoth were truly impossible, their existence would distort these distributions in obvious ways. So far, the distributions can accommodate them, but only just. This tension is productive. It pushes theorists to refine models of star formation, particularly under extreme conditions. It encourages observers to search for additional examples to determine whether Behemoth is a rare outlier or part of a previously hidden population. Measuring the unmeasurable also involves acknowledging what cannot yet be resolved. There are limits to resolution, even with the most advanced instruments. There are assumptions embedded in models that may need revision. There are physical processes, like magnetic fields and turbulence, that are difficult to include fully in simulations. Science progresses not by pretending these limitations do not exist, but by mapping them clearly. One of the quieter strengths of astrophysics is its transparency about uncertainty. Mass estimates are presented with ranges, confidence levels are stated, alternative interpretations are discussed openly. This does not weaken conclusions, it strengthens them. When multiple methods, each with different assumptions and sources of error, converge on similar results, confidence grows. That convergence is what makes Behemoth difficult to dismiss. The act of measurement then becomes an act of constraint rather than precision. Astronomers may not know the exact mass to the nearest percent, but they can say with increasing confidence that it exceeds previous expectations. In doing so, they shift the conversation from "is this possible?" to "under what conditions is this possible?" That shift opens new avenues of inquiry. It prompts questions about early star formation in the universe, when conditions were denser and more chaotic. It raises the possibility that the first generations of stars may have routinely exceeded mass limits we once thought universal. It also forces a re-examination of feedback processes. How does radiation pressure interact with inflowing gas in three-dimensional turbulent environments? How do magnetic fields alter accretion flows? How does rotation delay or accelerate mass loss? These are not idle questions. They shape how galaxies evolve, how heavy elements are distributed, and how black holes are seeded. As you sit with this, it may help to notice how indirect knowledge can still be robust. No one has touched Behemoth. No one has seen its surface. And yet, through careful interpretation of light, we can say meaningful things about its nature. This is not guesswork. It is disciplined imagination, constrained by physics and refined by observation. What forces are at work inside the Behemoth? How does gravity avoid being overwhelmed by the very light the star produces? At this point in the story, it is tempting to lean on a dramatic phrase, a star that breaks the rules, a star that defies physics, a star that should not exist. Those phrases appear in headlines because they feel satisfying. They offer a sense of rebellion, as if the universe itself has decided to misbehave. In reality, the situation is quieter and more interesting. Behemoth does not exist outside the laws of physics. It exists uncomfortably close to the edges of them, and that distinction matters, because it tells us less about cosmic rebellion and more about the limits of our understanding. For decades, astronomers believed they had a reliable answer to a fundamental question: how massive can a star be before it tears itself apart? The answer was not arbitrary. It came from balancing two forces that define stellar existence from birth to death. Gravity pulls inward, radiation pushes outward. Everything a star does is shaped by that tug of war. As mass increases, gravity strengthens, compressing the star's core. Compression raises temperature. Higher temperatures accelerate nuclear fusion. Fusion releases energy. Energy becomes radiation pressure. Radiation pressure pushes back. At some point, according to long-standing calculations, the push should become overwhelming. This threshold is often discussed in terms of limits rather than absolutes. Above a certain mass, stars are expected to lose material so rapidly that further growth becomes impossible. They shed gas through powerful winds. They blow away their own fuel supply. They regulate themselves downward. In that sense, the idea of an upper mass limit was never that stars could not exceed it momentarily, but that they could not remain there long enough to matter. Behemoth challenges the comfort of that expectation. It is not merely large, it is persistently large. Its luminosity, temperature, and inferred gravity all suggest a mass that lives right at the boundary where stability becomes questionable. And yet, the star exists. It burns, it radiates, it holds together. This forces a reframing of what shouldn't exist actually means. In physics, shouldn't usually translates to should be unstable. An instability does not mean instant destruction. It means a state that cannot last indefinitely, but may persist for a time, sometimes longer than intuition expects. Think of a tall stack of objects. At a certain height, the stack becomes unstable. That does not mean it collapses immediately. It may sway, it may lean, it may hold for a while before falling. During that time, it exists, even if it is living on borrowed balance. Behemoth appears to be such a structure. The star's interior is likely a place of constant adjustment. Fusion reactions surge. Radiation pressure fluctuates. Material flows outward in powerful winds. Gravity responds. The star is not static, it is dynamic, continuously negotiating its own survival. What makes this negotiation remarkable is not that it happens, but that it can happen at such scale. Older models often assumed a degree of symmetry and smoothness that reality does not always provide. They treated stars as roughly spherical, steadily radiating objects with well-behaved interiors. Those assumptions work well for many stars, including our Sun. At extreme masses, they begin to fray. Massive stars rotate rapidly. Rotation alters gravity across the star's surface. The equator experiences weaker effective gravity than the poles. This allows material to remain bound more easily in some regions than others. Rotation also enhances internal mixing, transporting fresh fuel into the core and delaying exhaustion. In effect, rotation can cheat the clock. Behemoth may be exploiting this loophole. If the star is rotating fast enough, its internal structure could support greater mass before radiation pressure overcomes gravity completely. This does not make the star stable in the long term. It makes it viable for longer than expected. There is also the role of geometry. Radiation pressure does not necessarily act uniformly in all directions. In a complex rotating star with strong magnetic fields and turbulent flows, energy may escape preferentially along certain paths. This uneven escape can reduce the effective outward push in other regions, allowing accretion or retention of mass to continue. Earlier models often treated radiation pressure as an evenly distributed force. Real stars are not so polite. Then there is the environment. Behemoth did not form in isolation. It formed in a dense stellar nursery, surrounded by enormous quantities of gas. In such environments, accretion flows can be chaotic, clumpy, and persistent. Rather than a smooth inflow of material, gas may arrive in bursts, overwhelming radiation pressure intermittently. In that scenario, the star grows in fits and starts, gaining mass faster than it can shed it, at least for a time. This matters because many theoretical limits assume steady conditions. The universe often operates in bursts. When these factors are combined, rapid rotation, asymmetric radiation, turbulent accretion, dense environments, the idea of a strict upper mass limit softens. The boundary becomes a region rather than a line. Behemoth appears to be inhabiting that region. Calling it a star that should not exist is therefore a shorthand. What it really means is that Behemoth exists where our models become less certain. It exposes the assumptions baked into those models and asks whether they hold under extreme conditions. This is not the first time astronomy has faced such a moment. White dwarf stars once appeared to defy gravity until electron degeneracy pressure was understood. Neutron stars seemed impossible until nuclear forces entered the picture. Black holes were dismissed as mathematical curiosities before evidence piled up. Each time, the universe did not violate physics. It revealed more of it. Behemoth may be doing something similar, but at a gentler scale. Instead of demanding new forces, it may require better accounting of known ones. Rotation, turbulence, geometry, time dependence. There is also the question of duration. Behemoth may not last long in this extreme state. Its current mass could be a fleeting snapshot. In a few 100,000 years, or less, the star may shed enough material to fall back into more familiar territory. Or it may collapse dramatically, ending its life in an event that reshapes its surroundings. From a cosmic perspective, this is brief. From our perspective, it is still real. The universe is under no obligation to make its rare events easy to observe. The fact that we are seeing Behemoth at all suggests that such states may be more common than previously thought, but short-lived enough to evade detection until now. This has implications beyond a single star. If stars can reach such masses, even temporarily, then early galaxies, where gas densities were higher and star formation more intense, may have produced many such giants. Their deaths could have seeded black holes far larger than expected, accelerating the growth of galactic cores. This line of thinking has been gaining traction, as astronomers struggle to explain how supermassive black holes appeared so early in the universe's history. If Behemoth-like stars were more common in the past, they could provide a missing link. In that sense, a star that shouldn't exist becomes a star that helps explain why other things do exist. There is also a more subtle discomfort that Behemoth introduces. It reminds us that theoretical limits are often provisional. They are not declarations of impossibility. They are reflections of current understanding. Physics does not hand us rules carved in stone. It hands us models that work within known conditions. When new conditions are observed, models must stretch or be refined. This is not failure. It is the process working as intended. It is also worth acknowledging the emotional component of this moment. Scientists are human. They grow accustomed to frameworks that feel stable. Discoveries that push against those frameworks can be unsettling, even when exciting. Behemoth provokes that mixture of fascination and caution. There is excitement in seeing something so extreme. There is also restraint, an awareness that early interpretations can shift as more data arrives. The balance between openness and skepticism is delicate. What keeps Behemoth in focus is not hype, but consistency. Multiple observations, multiple methods, and multiple teams converge on a picture that does not dissolve. The star should not exist if earlier assumptions were universally true. It does exist, which tells us those assumptions had limits. Deep inside a star like Behemoth, nothing is ever still. There is no quiet centre, no calm equilibrium where forces rest politely in balance. Instead, everything is in motion, pressed together, pulled apart, and constantly renegotiated. To understand why a star of this size can exist at all, even briefly, we have to focus on the most fundamental struggle shaping its life: the contest between gravity and radiation. Gravity is familiar. It is the force that pulls matter together, the reason stars form in the first place. Vast clouds of gas drift through space until a small imbalance appears. A region becomes slightly denser than its surroundings. That density attracts more material. The attraction grows stronger. Collapse begins. Given enough mass and time, gravity wins and a star ignites. Radiation pressure is less intuitive. It does not feel like a force in everyday life, but at stellar scales, it becomes impossible to ignore. Radiation pressure comes from light itself. Photons carry momentum. When they are emitted from a hot, dense core and interact with matter, they push. In most stars, this push is modest compared to gravity. It helps support the star internally but does not threaten its overall structure. In extremely massive stars, radiation pressure becomes dominant. Behemoth lives in that regime. At its core, nuclear fusion converts hydrogen into helium and heavier elements. This process releases enormous amounts of energy. That energy moves outward, first as radiation, then as heat, and finally as light escaping the star's surface. Every photon streaming outward carries momentum. Collectively, those photons exert pressure on the surrounding material. As mass increases, fusion accelerates. As fusion accelerates, radiation pressure intensifies. Eventually, radiation pressure becomes strong enough to compete directly with gravity's inward pull. This balance is not abstract. It determines whether a star grows, stabilizes, or begins to lose mass. For a long time, astronomers assumed that radiation pressure would impose a strict upper limit on stellar mass. The reasoning was straightforward. Beyond a certain point, the outward push of radiation should exceed gravity's ability to hold material in. Gas trying to fall onto the star would be blown away. The star would regulate itself, shedding mass faster than it could gain it. That logic still holds, but reality adds layers. Radiation pressure does not act uniformly. It depends on how light interacts with matter, and that interaction depends on composition, density, geometry, and motion. In a real star, none of these are perfectly uniform. Consider opacity, the measure of how easily radiation passes through material. In some regions of a star, matter may be more transparent to radiation. Photons slip through with little interaction. In other regions, opacity is higher. Photons collide with atoms and electrons, transferring momentum more effectively. If radiation escapes preferentially through lower opacity channels, pressure may be relieved unevenly. Instead of pushing outward everywhere equally, radiation finds paths of least resistance. This can allow gravity to continue pulling material inward along other directions. This uneven escape is one reason stars can exceed simple theoretical limits. Rotation amplifies this effect. Behemoth almost certainly rotates rapidly. Rapid rotation changes how gravity is distributed across the star. At the equator, centrifugal forces counteract gravity more strongly. At the poles, gravity remains stronger. This leads to an uneven surface, bulging at the equator and compressed at the poles. Radiation responds to this geometry. Energy escapes more readily along the poles, where gravity holds material more tightly and opacity conditions differ. The result is an anisotropic radiation field. Light does not push equally in all directions. In practical terms, this means radiation pressure can vent itself without completely halting accretion or tearing the star apart. Earlier models often assumed spherical symmetry for simplicity. That assumption works well for many stars, but it becomes less reliable as mass and rotation increase. Behemoth exists precisely where those simplifying assumptions begin to fail. Another important factor is time. Radiation pressure builds as fusion accelerates, but accretion does not stop instantaneously. Gas in a dense stellar nursery does not fall in smoothly. It arrives in clumps, filaments, and bursts. During these bursts, gravity can overwhelm radiation locally, allowing material to reach the star's surface before being pushed away. This stop-and-go growth can push a star beyond equilibrium limits temporarily. The star grows faster than radiation pressure can respond, at least for a while. Behemoth may be the result of such a process. A star that grew rapidly in an exceptionally dense environment, reaching a mass that places it at the edge of stability before radiation-driven mass loss can bring it back down. Once the star reaches this extreme state, the struggle intensifies. Radiation pressure does not simply push outward gently, it drives powerful stellar winds. These winds carry mass away from the star at enormous speeds. In Behemoth's case, the mass loss rate is likely extraordinary, perhaps thousands of times greater than that of the Sun. This mass loss is not uniform or constant. It can vary with time, responding to changes in fusion rate, rotation, and internal structure. The star sheds layers, exposing hotter regions beneath, which in turn alters radiation output. It is a feedback loop. Gravity tries to compress the core further. Compression raises temperature. Temperature increases fusion. Fusion increases radiation pressure. Radiation pressure strips mass. Mass loss reduces gravity's grip. The balance shifts again. For smaller stars, this feedback settles into a stable rhythm. For stars like Behemoth, it may never truly settle. The star exists in a state of ongoing adjustment, never fully at rest. This raises an important point. Stability does not mean inactivity. It means persistence over time despite internal change. Behemoth may be stable in the sense that it persists, not because its internal forces are calm, but because they remain in a dynamic balance. That balance may be temporary, but temporary in astrophysics can still mean hundreds of thousands of years. Another layer to consider is composition. The interaction between radiation and matter depends on what the matter is made of. Elements heavier than hydrogen and helium, collectively called metals in astronomical terms, increase opacity. Higher opacity strengthens radiation pressure by increasing photon interactions. Stars forming in environments with lower metal content may behave differently. In the early universe, metals were rare. Radiation pressure would have been less effective at pushing material away, potentially allowing stars to grow even larger. Behemoth's composition offers clues about whether it formed in a metal-rich or metal-poor environment. Webb's spectral observations can probe this, revealing the presence of heavier elements in the star's atmosphere. If Behemoth formed in a relatively low metallicity environment, that could partially explain its mass. Radiation pressure would have been less efficient at limiting growth during formation. This connection between composition and size is not academic. It ties the existence of stars like Behemoth to cosmic history. The universe has not always had the same chemical makeup. Conditions for star formation have evolved. The struggle between radiation pressure and gravity, therefore, is not fixed across time. It depends on when and where a star forms. This makes Behemoth more than a curiosity. It becomes a probe of stellar physics under extreme conditions. One might ask why the star does not simply explode under such stress. The answer lies in timescales. Explosions occur when internal support fails catastrophically. Behemoth's internal adjustments, while violent, may still operate on timescales slow enough to avoid immediate collapse. Eventually, though, something will give. As fusion progresses, the star will build heavier elements in its core. Each new fusion stage releases less energy per unit mass. Radiation pressure may weaken relative to gravity. When iron forms in the core, fusion can no longer provide support. At that point, gravity will win decisively. What happens next depends on the star's mass at collapse. It may explode as a supernova, it may collapse directly into a black hole, or it may do something in between, shedding outer layers while the core vanishes. But that moment lies ahead. Right now, Behemoth exists in the space between formation and destruction, held together by a balance that feels almost precarious. Radiation pushes outward with relentless force. Gravity pulls inward with equal determination. Neither yields easily. This balance is the reason the star can exist at all, and the reason its existence feels surprising. Understanding this struggle also reframes how we think about limits. The universe does not enforce them cleanly, it explores them. It allows objects to approach, cross, and linger near boundaries, testing what can persist. Behemoth is one such test. Speed defines everything about a star like Behemoth. Not the speed at which it moves through space, though that may be considerable, but the speed at which it consumes itself. Mass buys power, but it does not buy time. In fact, it does the opposite. For smaller stars, longevity is almost boring. A red dwarf can shine for trillions of years, sipping hydrogen slowly, converting mass into energy at a measured pace. Even our Sun, which feels vast and powerful from Earth, is expected to live for roughly 10 billion years. It burns steadily, balancing gravity and radiation without drama. Behemoth has no such patience. The relationship between mass and lifespan in stars is deeply counterintuitive. One might assume that more mass means more fuel and therefore a longer life. In ordinary circumstances, that logic works. A larger car with a bigger fuel tank can drive farther. Stars do not follow that analogy. As stellar mass increases, luminosity increases far more rapidly. A star 10 times the mass of the Sun is not merely 10 times as bright, it may be thousands of times brighter. A star 100 times the Sun's mass can outshine it by millions. Brightness in this context means energy output per second. Every second, Behemoth releases staggering amounts of energy. That energy comes from nuclear fusion in its core. Hydrogen nuclei are forced together under extreme pressure and temperature, forming helium and releasing energy in the process. The faster fusion runs, the faster fuel disappears. Behemoth's core is a furnace operating at extraordinary intensity. Temperatures likely reach tens of millions of degrees. Pressure compresses matter to densities that are difficult to imagine outside of mathematics. Under these conditions, fusion does not proceed gently. It roars. As a result, the star burns through its hydrogen fuel at an astonishing rate. Instead of lasting billions of years, a star of Behemoth's mass may live only a few million years, perhaps less. In cosmic terms, this is brief. If the Sun's life was stretched to the span of a human lifetime, Behemoth's would last only a few days. This imbalance between size and duration shapes everything about its existence. High mass means high gravity. High gravity means intense compression. Intense compression means elevated core temperatures. Elevated temperatures mean accelerated fusion. Accelerated fusion means immense radiation pressure and mass loss. The chain is direct and unforgiving. Living fast is not optional at this scale, it is required. There is also the matter of internal structure. Smaller stars like the Sun have radiative cores and convective outer layers. Energy produced in the core travels outward gradually, sometimes taking hundreds of thousands of years to reach the surface. In extremely massive stars, convection can dominate the interior. Material circulates vigorously, hot plasma rises, cooler plasma sinks, energy moves more efficiently. Fresh hydrogen is mixed into the core more readily. This mixing prolongs hydrogen burning slightly, but it also ensures that the star remains intensely active throughout its structure. There are no quiet zones. As hydrogen becomes depleted in the core, the star does not fade gently. It shifts to fusing heavier elements. Helium fuses into carbon and oxygen. Carbon may fuse into neon and magnesium. Each stage burns hotter and faster than the last. The progression accelerates toward collapse. For Behemoth, this chain may unfold with exceptional speed. Each fusion stage may last a fraction of the time seen in lower mass stars. The core contracts, heats, ignites new fuel, and moves forward. The star becomes layered internally like an onion, with different fusion processes occurring in shells around the core. This layered structure is inherently unstable in massive stars. Energy output fluctuates, stellar winds intensify. The outer layers may expand and contract. Some extremely massive stars enter phases known as luminous blue variables, where they undergo dramatic mass ejections. Entire shells of material can be expelled into surrounding space. If Behemoth enters or is currently in such a phase, its appearance and mass could change significantly over relatively short timescales. Burning bright also means influencing the environment aggressively. Behemoth's radiation ionizes nearby gas, stripping electrons from atoms and creating vast regions of glowing plasma. These ionized regions expand outward, shaping the surrounding molecular cloud. In some areas, radiation compresses gas, triggering new star formation. In others, it erodes material, halting collapse. The star is not merely consuming itself, it is reshaping its neighborhood. This environmental impact is not subtle. Stellar winds from massive stars carve cavities in gas clouds. Shock fronts propagate outward. Over time, the combined effects of multiple massive stars can disrupt entire star-forming regions. In clusters where behemoth-like stars exist, the collective radiation may halt star formation entirely after a short burst of activity. The giants burn fiercely, then extinguish the very conditions that allowed them to form. There is something almost self-limiting about this process. The same intensity that creates Behemoth also ensures that such stars cannot dominate indefinitely. They blaze, disrupt, and vanish, leaving behind altered landscapes. The final stage of this accelerated life is collapse. When the core builds up iron, fusion can no longer produce energy. Iron fusion consumes energy rather than releasing it. At that moment, radiation pressure can no longer counteract gravity. The core collapses in a fraction of a second. For stars of moderate mass, this collapse rebounds, producing a supernova explosion that ejects outer layers into space. For stars at the highest masses, the story becomes less certain. If Behemoth retains enough mass at collapse, gravity may overwhelm everything. The core could collapse directly into a black hole, swallowing much of the star without a spectacular explosion. Alternatively, it could produce an extremely energetic supernova, possibly a pair instability supernova, in which the star is completely destroyed, leaving no remnant. The outcome depends sensitively on mass, rotation, and internal composition at the moment of collapse. Living fast means dying decisively. The heavy elements forged in Behemoth's core, carbon, oxygen, silicon, iron, will not remain confined forever. Whether through wind-driven mass loss or explosive death, they will be dispersed into the surrounding medium. These elements become the raw material for future generations of stars and planets. In that sense, Behemoth's short life contributes to long-term cosmic evolution. There is also an observational aspect to this speed. Because such stars live briefly, they are rare at any given time. The universe may produce many of them over billions of years, but catching one during its active phase is statistically unlikely. This rarity amplifies the significance of each confirmed example. Behemoth's existence suggests that extreme star formation is not purely theoretical. It occurs often enough that we can observe it, even if briefly. Another consequence of rapid burning is variability. Massive stars can pulsate. Their outer layers may expand and contract rhythmically. Changes in brightness may occur over timescales ranging from days to years. Monitoring such variability provides additional clues about internal structure and stability. Webb and other observatories can track these changes, refining models further. Variability patterns may confirm rotation rates, wind strengths, and mass loss mechanisms. All of this reinforces the idea that Behemoth is not a static monument in space. It is an evolving system, racing toward an inevitable transformation. There is a subtle comfort in this understanding. The universe does not create giants casually. It creates them in conditions that justify their existence and removes them swiftly when their role is complete. Behemoth's life, intense and brief, may shape regions far beyond its immediate surroundings. Its death may seed black holes or distribute heavy elements that one day participate in entirely new systems. Light is easy to underestimate, In everyday life, it feels weightless, intangible, something that illuminates without pushing back. You can stand in sunlight all day and never feel it shove you across a room. Because of that, it is tempting to think of light as passive, a byproduct rather than an active participant in the universe. At the scale of Behemoth, that intuition fails completely. Here, light is not just illumination, it is force. It carries momentum, and that momentum matters. Enough of it, moving in one direction, can oppose gravity, strip matter from a star, and reshape entire regions of space. In extreme stars, light does not merely escape, it pushes. The idea that light has weight, or at least something functionally similar, comes from a simple but profound principle. Photons, despite having no rest mass, carry energy. Energy and momentum are linked. When photons interact with matter, they transfer that momentum. The result is pressure. This radiation pressure is negligible on human scales. It becomes noticeable only when enormous numbers of photons are involved. A star like Behemoth produces not just many photons, but an incomprehensible flood of them. Every second, more light leaves its surface than our sun will emit in many years. That flood presses outward constantly. Inside the star, radiation pressure contributes to internal support, helping counteract gravity's inward pull. Near the surface, it becomes something more dramatic. It accelerates particles, drives winds, and in some cases peels entire layers of the star away. This is not a metaphor, it is measurable. Astronomers observe the effects of radiation pressure through broadened spectral lines, signatures of material racing away from the star at high speed. These winds are not gentle. In Behemoth's case, they may reach thousands of kilometers per second, carrying vast amounts of mass into surrounding space. The star is losing weight because light is pushing it away. What makes this particularly interesting is that radiation pressure does not act on all matter equally. It interacts most strongly with electrons and ions. When photons collide with free electrons, they impart momentum efficiently. In hot, ionized environments like Behemoth's atmosphere, this interaction becomes dominant. The higher the luminosity, the stronger the effect. There is a critical point where radiation pressure can balance gravity exactly. At that point, a star sits at what is often called a luminosity limit. Push beyond it, and radiation pressure overwhelms gravity, driving mass loss aggressively. Behemoth appears to be operating near, or perhaps beyond, this threshold. This is one reason its mass does not increase indefinitely. Even if gravity pulls inward, light pushes back. The star regulates itself not by remaining static, but by shedding material as fast as it forms or accretes it. This self-regulation is messy and dynamic. Light escaping from the core does not travel outward smoothly. It interacts with layers of plasma, scattering, being absorbed and re-emitted countless times. Each interaction transfers momentum. Over time, this builds into a sustained outward force. In smaller stars, this force is modest. In Behemoth, it becomes one of the dominant drivers of evolution. There is also a directional aspect to this pressure. As discussed earlier, Behemoth is almost certainly rotating rapidly. Rotation creates asymmetry. The star is not perfectly spherical. Gravity is weaker at the equator, stronger at the poles. Radiation responds to this imbalance. Light escapes more easily along certain directions. Where gravity holds material tightly, radiation can vent outward more efficiently. Where gravity is weaker, radiation pressure more easily lifts material away. The result is structured mass loss. Rather than losing matter evenly, Behemoth may produce bipolar outflows, strong winds focused along specific axes. Over time, these outflows carve shapes into the surrounding gas, leaving imprints that astronomers can observe long after the star itself has changed or disappeared. This is one way massive stars leave fingerprints on their environment. Another subtlety lies in the interaction between radiation pressure and dust. While Behemoth's immediate surroundings are likely too hot for dust to survive close to the star, dust exists farther out in the surrounding cloud. Light from the star pushes on dust grains very effectively. Those grains, in turn, drag gas along with them. This coupling allows radiation pressure to influence material well beyond the star's surface. In star-forming regions, this effect can halt further accretion. As Behemoth shines, it may prevent nearby gas from collapsing into additional stars. Its light clears space, creating cavities and halting growth in its immediate vicinity. At the same time, shock fronts created by radiation-driven winds can compress gas farther away, triggering new star formation at the edges. Light, therefore, can both suppress and promote creation, depending on geometry and timing. This dual role is one of the reasons massive stars are such influential architects of galaxies. The weight of light also plays a role in determining Behemoth's fate. As long as fusion continues, radiation pressure provides internal support. But fusion fuel is finite. When lighter elements are exhausted, radiation pressure weakens. Gravity then gains the upper hand. The timing of this transition matters. If Behemoth loses enough mass through radiation-driven winds before collapse, it may avoid certain catastrophic outcomes. If it retains too much mass, collapse becomes unavoidable and extreme. Light therefore shapes not only the star's life, but its death. It is worth pausing on how counterintuitive this is. Something that feels insubstantial, something you can block with your hand, is powerful enough to sculpt stars. Yet this principle is not confined to astrophysics. Solar sails, thin reflective sheets proposed for spacecraft propulsion, rely on radiation pressure from sunlight. The force is tiny, but over time, in the vacuum of space, it accumulates. Behemoth is a solar sail in reverse. Instead of being pushed by an external source of light, it is being pushed by its own output. This self-interaction is part of what makes massive stars unstable. They generate the very force that undermines their ability to hold themselves together. There is also a feedback between radiation pressure and internal mixing. As mass is lost from the surface, internal layers are exposed. New regions experience different pressures and temperatures. Fusion rates adjust. Radiation output changes. The star constantly recalibrates itself. Because of this, mass estimates are snapshots, not fixed values. Behemoth today may not be Behemoth tomorrow. Its true scale shifts as light pushes matter away. This complicates observation. When astronomers say Behemoth has a certain mass, they're capturing it in mid-struggle. The number is real, but it is not permanent. In a sense, Behemoth is defined less by its size than by its rate of change. The concept of light having weight also extends beyond individual stars. In extreme environments near black holes, radiation pressure can limit how fast matter falls in. This sets accretion limits similar in spirit to stellar mass limits. The same physics appears at different scales. That connection matters because Behemoth may be a stepping stone in understanding how black holes grow. If massive stars can exist briefly above expected limits, then their collapse could see black holes more massive than previously assumed. Radiation pressure, by regulating stellar mass loss, indirectly regulates black hole birth. This is why Behemoth's light matters beyond its own life. There is also a philosophical angle that is difficult to ignore. Light is often associated with clarity, revelation, and information. In Behemoth's case, light is also erosion. It strips, sculpts, and limits. The same photons that allow us to observe the star are actively working to dismantle it. This symmetry is not poetic, it is literal. Every observation of Behemoth is made possible by light that escaped. That escape required momentum transfer. That momentum contributes infinitesimally to the star's mass loss. Observation and evolution are linked through the same physical process. As we continue deeper into this story, the consequences of such intense radiation extend outward. Light does not stop at the star's surface. It travels into surrounding space, shaping entire systems. Understanding how Behemoth compares to other stars, how its light stacks against more familiar benchmarks, helps anchor this abstract force in something the mind can hold on to. That comparison between the extreme and the familiar is where our attention naturally drifts next, because scale only becomes meaningful when placed side by side with something we know. Try, for a moment, to anchor everything you know about stars to a single reference point. Not an abstract number or a diagram in a textbook, but the one star that quietly defines your daily life, the sun. Every sense of stellar scale you have, whether you realize it or not, begins there. The sun feels enormous because it is enormous relative to us. Its diameter is about 100 times that of Earth. More than 1 million Earths could fit inside it. Its mass dominates the solar system so completely that everything else is, in gravitational terms, an afterthought. Planets trace their paths because the sun tells them to. Comets fall inward because the sun allows it. Even distant icy bodies feel its influence. For most conversations, that is where scale ends. But in stellar physics, the sun is not the upper end of anything. It is a baseline, a comfortable, middle-aged, well-behaved reference star that happens to be close enough for us to study in detail. In the broader population of stars, the sun sits firmly in the middle. Not small, not large, not extreme. Behemoth exists so far beyond this baseline that comparisons quickly become uncomfortable. Start with mass. The sun defines one solar mass, the unit astronomers use to compare stars. Behemoth's estimated mass is not a few times larger. It is tens, possibly more than 100 times that reference. This difference is not additive, it is transformative. Doubling a star's mass does not simply double its brightness or energy output. The relationship is far steeper. As mass increases, luminosity increases disproportionately. A star 10 times the sun's mass can be thousands of times brighter. At Behemoth scale, brightness becomes almost absurd to express in everyday terms. If Behemoth were placed where the sun is now, the solar system would not survive in any recognizable form. The radiation alone would strip atmospheres from planets. Stellar winds would erode surfaces. Orbits would be destabilized by mass loss and intense gravitational tides. This is not exaggeration. It is a reflection of how radically different such stars are. Consider size in terms of radius. The sun's radius is about 700,000 kilometers. Behemoth's radius depends on its current evolutionary state, but it could be dozens of times larger. In some phases, massive stars expand dramatically, becoming supergiants with radii that would engulf the orbit of Mercury, Venus, and possibly Earth. Yet even that comparison has limits. A star's radius does not tell the full story. Massive stars are less dense on average than the sun. They are puffed up by radiation pressure, with outer layers that are tenuously bound. Their gravity at the surface can be weaker than that of smaller, denser stars, even though their total mass is far greater. This counterintuitive structure is part of what allows Behemoth to shed mass so effectively. Its outer layers are easier to lift away. Light pushes, matter leaves. Temperature adds another layer of contrast. The sun's surface temperature is about 5,800 Kelvin. Behemoth's surface temperature is likely far higher, possibly tens of thousands of Kelvin. This difference shifts where most of the star's energy is emitted. The sun shines primarily in visible light. Behemoth emits a significant fraction of its energy in ultraviolet and infrared. That shift matters because ultraviolet radiation is particularly effective at ionizing gas and driving chemical change. Behemoth's surroundings are bathed in radiation capable of stripping electrons from atoms, altering the state of matter over large volumes of space. From the perspective of nearby material, Behemoth is not just bright, it is aggressive. Now consider time. The sun has existed for about 4.6 billion years and is expected to shine for another 5 billion or so. Its life unfolds slowly. Changes occur on timescales that dwarf human history. Behemoth does not offer that luxury. Its entire lifespan may be shorter than the time since early humans began using tools. Its most extreme phases could last only a few 100,000 years. This compression of time is part of what makes massive stars rare. They exist briefly, burn intensely and vanish. The universe does not hold on to them for long. When astronomers compare Behemoth to the Sun, they're not just comparing size, they're comparing modes of existence. The Sun is stable, predictable, and steady. Behemoth is volatile, intense, and transient. Energy output provides another stark contrast. Every second, the Sun emits about 3.8 times 10 to the power of 26 watts of power. That number is so large it already strains comprehension. Yet Behemoth likely emits millions of times more energy per second. Each second of its life represents an energy release that would take the Sun many years to match. This energy is not abstract. It manifests as radiation, stellar winds, and dynamic interaction with the surrounding medium. Imagine scaling that down into something relatable. If the Sun were a quietly burning campfire, Behemoth would be a roaring industrial furnace. Both burn fuel, both produce light and heat. The difference lies in intensity and consequence. There is also a psychological aspect to this comparison. Humans tend to imagine stars as scaled-up versions of the Sun. Bigger ball, brighter glow, same basic idea. That intuition works reasonably well until mass crosses certain thresholds. Beyond those thresholds, stars stop behaving like scaled-up suns and start behaving like fundamentally different objects. Behemoth is not just a bigger sun. It is a different category of star. Its internal structure is dominated by convection. Its mass loss shapes its evolution more than its internal fuel supply. Its rotation influences everything from luminosity to stability. Its death will be qualitatively different, are treated as mere extensions of solar-type stars. Models will fail. Their feedback, their lifetimes, and their remnants will be misrepresented. Recognizing them as a distinct regime of stellar physics is essential. Comparisons to the Sun also highlight how special our star is, in a quiet way. The Sun is massive enough to support a stable planetary system, but not so massive that it burns out quickly or destabilizes its surroundings. It produces light and heat gently enough to allow complex chemistry to persist over billions of years. Behemoth offers no such environment. Its presence would sterilize nearby space long before planets could settle into stable conditions. If planets formed at all, they would be battered relentlessly by radiation and wind. This is not a criticism of Behemoth. It is simply a consequence of scale. Stars like Behemoth are not cradles of life. They are engines of change. They forge heavy elements rapidly. They inject energy into galaxies. They shape star formation on large scales. Their role is not to host calm systems, but to transform environments. This perspective helps explain why galaxies look the way they do. Spiral arms glow because of massive stars. Nebulae are carved by their radiation. Supernova remnants mark where such stars ended their lives. The heavy elements found in planets and organisms owe their existence in part to stars that lived fast and died violently. Comparing Behemoth to the Sun, then, is not about diminishing one or glorifying the other. It is about recognizing diversity. The universe does not produce a single kind of star. It produces a spectrum, from small, long-lived red dwarfs to massive, short-lived giants. Each plays a role. Each occupies a niche defined by physics. Behemoth occupies an extreme niche. This comparison also helps ground the idea of true scale. Without a familiar anchor, numbers drift. With the Sun as reference, Behemoth's size becomes less abstract, even if still difficult to visualize. It also clarifies why the discovery matters. If Behemoth were only marginally larger than the Sun, it would not challenge theory. If it were only slightly more massive than known giants, it would not demand revision. What makes it important is how far beyond familiar benchmarks it appears to sit. Scale beyond the Sun forces us to reconsider what is typical and what is possible. As our understanding deepens, comparisons will extend further. Behemoth will be weighed against other massive stars, against clusters, and eventually against the structures they leave behind. Its scale will be contextualized not only in terms of size, but in terms of influence. That influence does not stop with the star itself. The mass, energy, and momentum Behemoth injects into its surroundings ripple outward, subtly affecting how space and time behave nearby. Extreme mass does not merely sit there. It bends, it shapes, it leaves imprints. Mass does more than pull. When it becomes extreme, it quietly alters the stage on which everything else happens. Space itself responds. Time follows. At the scale Behemoth occupies, these effects are subtle but real, woven into the star's existence whether we notice them or not. Relativity is often introduced through dramatic examples. Black holes, neutron stars, objects so dense that they bend light into loops and slow time to a crawl. Compared to those, a star, even a very large one, can seem almost ordinary. But relativity does not switch on only at catastrophe. It operates everywhere, all the time, its influence growing gradually with mass and density. Behemoth sits in an interesting middle ground. It is not compact enough to behave like a black hole. Its radius is enormous compared to its mass concentration, and yet its gravity is strong enough that relativistic effects are no longer completely negligible. They do not dominate its behaviour, but they whisper in the background, shaping details that classical physics alone would miss. To understand this, it helps to return briefly to the idea that gravity is not just a force. According to Albert Einstein, gravity is the curvature of space-time caused by mass and energy. Objects move the way they do not because they are pulled along invisible lines, but because space-time itself is shaped by what exists within it. The more mass you pack into a region, the more pronounced that curvature becomes. Behemoth, by virtue of its sheer mass, creates a deeper curvature in space-time than most stars. This curvature affects how light escapes, how particles move near the star, and how time flows in its immediate vicinity. The effect on time is small, but measurable in principle. Clocks closer to a massive object tick slightly more slowly than clocks farther away. This phenomenon, known as gravitational time dilation, has been measured near Earth using atomic clocks separated by mere centimetres in altitude. Near Behemoth, the effect would be stronger, though still subtle compared to extreme objects like black holes. Processes occurring deep within the star unfold in a slightly different temporal rhythm than those farther out. From the outside, these differences blur together, but they exist. Light too feels the curvature. Photons climbing out of Behemoth's gravitational well lose a tiny fraction of their energy. Their wavelengths stretch slightly, a process called gravitational redshift. For most stars, this effect is minuscule. For Behemoth, it is still small, but no longer trivial. Spectral lines observed by telescopes carry the imprint of this redshift. By measuring it carefully, astronomers can infer aspects of the star's gravitational field, offering yet another indirect probe of its mass. This is one of the quieter ways relativity enters the measurement process. There is also the question of how gravity and radiation interact when both are extreme. In Newtonian physics, gravity and light are largely separate considerations. In relativistic physics, energy itself contributes to gravity. Light carries energy. Energy curves space-time. In Behemoth, the energy density inside the star is enormous. The radiation trapped within its interior contributes, in a small but non-zero way, to the overall gravitational field. This effect is tiny compared to the contribution from mass, but at the margins it matters. It reinforces a subtle feedback loop. Fusion produces energy. Energy contributes to gravity. Gravity compresses matter. Compression fuels fusion. The loop tightens. For most stars, this loop is dominated by mass. For Behemoth, energy begins to join the conversation. Rotation complicates this picture further. Rapid rotation drags space-time slightly along with it, a phenomenon known as frame dragging. Around compact objects, this effect can be significant. Around stars, it is weaker, But again, Behemoth pushes the boundary where it becomes detectable. Frame dragging influences how material moves near the star. It can alter the structure of stellar winds, affect the trajectories of ejected matter, and subtly shape the environment over time. These are not dramatic distortions, they are refinements, corrections layered atop classical behaviour. This layered physics is part of what makes modelling Behemoth challenging. Stellar evolution codes must account for radiation pressure, rotation, mass loss, and increasingly relativistic corrections. Each addition complicates the equations but also brings them closer to reality. Why does this matter? Because Behemoth may represent a transitional regime, a place where stars are no longer well described by purely Newtonian physics, but not yet dominated by relativistic extremes. Understanding this regime helps bridge the gap between ordinary stars and the compact remnants they leave behind. It also has implications for what comes next. As Behemoth loses mass through winds, its gravitational field evolves. As fusion progresses, internal energy distribution changes. As the core contracts, relativistic effects strengthen. The star moves along a continuum toward collapse. If Behemoth eventually forms a black hole, the seeds of that transformation are already present. The curvature of space-time near its core will deepen. Time dilation will increase. Light will struggle more and more to escape. In this sense, Behemoth is not just a massive star, it is a prelude. Relativity also influences how we interpret observations across vast distances. Light leaving Behemoth travels through expanding space. Its wavelength stretches due to cosmic expansion. That cosmological redshift layers on top of gravitational redshift, and Doppler shifts from motion. Untangling these effects requires precision and care. Webb's instruments, combined with detailed models, allow astronomers to separate them, but only with effort. This disentangling is part of what makes modern astrophysics both powerful and painstaking. There is a temptation to think of relativity as something reserved for the most exotic corners of the universe. Behemoth reminds us that it permeates everything. It is not a special effect, it is the rule. The difference lies in degree, not kind. At human scales, relativistic effects are imperceptible. At stellar scales, they are faint but present. At the scale of collapse cores, they dominate. Behemoth sits along that gradient, offering a rare opportunity to study how gravity transitions from familiar to extreme. This is another reason its scale matters. By existing near the upper end of stellar mass, Behemoth allows astronomers to test where classical approximations begin to fail. It helps calibrate models that must eventually describe supernovae, black hole formation, and the behaviour of matter under immense stress. It also reframes our intuition. When we think of stars, we often imagine them as static lights in the sky. Relativity reminds us that they are dynamic distortions in space-time, each carving its own subtle shape into the universe. Behemoth carves a deeper groove than most. That groove affects how matter flows nearby, how light escapes, and how time ticks in its presence. These effects may be small, but over millions of years, small influences accumulate. What happens when mass and gravity finally overwhelm every form of support? What lies at the end of Behemoth's path? Eventually, every negotiation between gravity and resistance ends, not abruptly, not necessarily violently at first, but inevitably. For a star like Behemoth, the question is not whether collapse will happen, but how it will arrive, and what form it will take when it does. Collapse is often imagined as a single dramatic moment. A star runs out of fuel, implodes, and something catastrophic follows. The reality is more gradual and more conditional. Collapse is a process that begins long before anything visibly fails, woven quietly into the later stages of a star's life. For Behemoth, that process may already be underway. At its core, fusion proceeds through a sequence of fuels. Hydrogen becomes helium. Helium becomes heavier elements. Each step produces less usable energy than the one before. Early in a star's life, fusion provides abundant outward pressure. Later on, that support weakens, not suddenly, but progressively. The core grows heavier and denser. As heavier elements accumulate, the balance shifts. Fusion reactions require higher temperatures to proceed. Gravity responds by compressing the core further. Compression raises temperature, which ignites the next stage of fusion, but only briefly. Each successive stage burns faster than the last. This acceleration is unforgiving. For a star of moderate mass, these stages can unfold over millions of years. For Behemoth, they may compress into a much shorter span. The internal clock runs fast. There is little margin for pause. One of the key thresholds arrives when iron begins to form in the core. Iron is different. Fusing iron does not release energy, it consumes it. At that moment, fusion can no longer provide support. Radiation pressure falters. Gravity takes control. This is the beginning of true collapse. What happens next depends on several variables, and Behemoth sits at the center of uncertainty for all of them. Core mass, rotation rate, remaining envelope mass, internal composition. Even small differences in these parameters can lead to radically different outcomes. One possibility is direct collapse. In this scenario, Behemoth's core collapses under its own gravity, without producing a conventional supernova. The outer layers may fall inward as well, swallowed by the collapsing core. Little energy escapes. There is no dramatic explosion to announce the event across the galaxy. Instead, the star simply disappears, leaving behind a newly formed black hole. This outcome becomes more likely as mass increases. For extremely massive stars, the gravitational pull during collapse can be so strong that even the shock waves typically responsible for supernova explosions fail to propagate outward. Energy is trapped. Matter falls inward. The collapse is silent on cosmic scales. If Behemoth follows this path, it could form a black hole far more massive than typical stellar remnants. Such an object would help explain the existence of surprisingly large black holes in young galaxies, where there has not been enough time for smaller black holes to grow gradually. Another possibility is a catastrophic explosion. Under certain conditions, very massive stars can undergo a process known as pair instability. At extremely high core temperatures, energy converts into particle pairs, reducing radiation pressure suddenly. The core contracts rapidly, triggering runaway fusion that releases an enormous amount of energy. The result can be a supernova so powerful that the star is completely destroyed, leaving no remnant behind. Every atom is expelled into space. Whether Behemoth is massive enough and structured appropriately to undergo such an event remains uncertain. The boundaries between collapse and explosion are narrow and sensitive to detail. There is also an intermediate path. Behemoth may shed enough mass through radiation-driven winds before collapse to alter its fate. If the star loses a significant portion of its outer layers, the core mass at the moment of collapse may fall below certain thresholds. This could allow a supernova explosion to occur, leaving behind a neutron star or a smaller black hole. Mass loss, therefore, is not just a side effect of Behemoth's brightness. It is a determining factor in how the star ends. Rotation complicates this further. Rapid rotation can support the core against collapse for longer, flattening it and redistributing angular momentum. During collapse, this rotation can lead to asymmetric explosions or the formation of jets. In some cases, these jets may punch through the star's outer layers, producing energetic outbursts. Such processes are thought to be involved in some of the most energetic explosions observed in the universe. Whether Behemoth could produce such an event depends on how much angular momentum it retains until the end. The uncertainty here is not a weakness. It reflects the complexity of real stars. Astronomers model collapse using sophisticated simulations that incorporate gravity, nuclear physics, radiation transport, and fluid dynamics. Even with modern computing power, these simulations are challenging. Small changes in input parameters can lead to different outcomes. Behemoth sits in a regime where those sensitivities are amplified. This makes it an important test case. If Behemoth collapses directly, It supports models that predict silent black hole formation at high masses. If it explodes completely, it confirms the existence of pair instability supernovae at these scales. If it lands somewhere in between, it refines the boundaries between these possibilities. In all cases, the consequences extend beyond the star itself. A direct collapsed black hole could influence its surroundings for millions of years, accreting material and shaping galactic evolution. A complete explosion would enrich the surrounding space with heavy elements, seeding future stars and planets. Even partial explosions redistribute energy and matter on large scales. The question of collapse is therefore also a question of legacy. Behemoth's end will not be quiet in its effects, even if it is quiet in its appearance. Whatever remains, or whatever is expelled, will participate in the next cycle of cosmic evolution. There is also a human element to this question. For scientists, Behemoth represents an opportunity to observe a star near the upper edge of possibility before it vanishes. Massive stars do not announce their timelines clearly. Predicting exactly when collapse will occur is difficult. Observations capture moments, not schedules. This uncertainty adds urgency, but not haste. Astronomers monitor such stars patiently, gathering data over years, knowing that any new observation could reveal subtle changes hinting at internal shifts, brightness variations, spectral changes, wind behavior. Each offers clues. From a broader perspective, the question of collapse highlights something fundamental about the universe. Extremes are not stable destinations, they are transitions. Behemoth exists in transit between formation and disappearance. Its current state is not an endpoint, it is a passage. Long before a massive star reaches the moment of collapse, it has already rewritten the landscape around it. Not subtly, not passively, but through a steady accumulation of influence that spreads outward year after year. By the time a star like Behemoth ends its life, the region it was born into no longer resembles the place it started. This is what astronomers mean when they talk about cosmic feedback, the process by which stars do not merely exist inside galaxies, but actively sculpt them. To understand this, it helps to stop thinking of stars as isolated points of light, and start thinking of them as engines embedded in a larger system. A galaxy is not a quiet collection of stars drifting politely in space. It is a dynamic environment filled with gas, dust, radiation, magnetic fields, and motion. Stars form out of this material, but once they do, they immediately begin pushing back on it. Behemoth pushes harder than most. From the moment it ignited, its radiation began altering the physical state of its surroundings. Ultraviolet light flooded nearby gas, stripping electrons from atoms and creating vast regions of ionized plasma. These regions expand outward, driven by thermal pressure, reshaping the structure of the surrounding molecular cloud. Dense filaments are eroded, cavities form, boundaries sharpen. This is feedback in its earliest form. Ionization alone is enough to change the fate of nearby material. Gas that might otherwise have cooled and collapsed into new stars becomes heated and diffuse. Star formation is suppressed close to Behemoth, not because the material disappears, but because it is kept from settling. At the same time, the process is not uniformly destructive. As ionized regions expand, they push against cooler gas farther out. That compression can trigger collapse in those outer layers, igniting new rounds of star formation at the edges of the cavity. In this way, Behemoth both halts and initiates creation, depending on location and timing. This dual role is one of the defining features of massive stellar feedback. Radiation is only part of the story. Stellar winds add another layer of influence. Behemoth loses mass through winds driven by radiation pressure, ejecting enormous quantities of material at high speed. These winds collide with surrounding gas, creating shock fronts that propagate outward. Shock fronts heat gas, compress it, and stir turbulence. Over time, this turbulence can prevent gas from settling into stable configurations. It keeps star-forming regions chaotic, delaying collapse in some places while enhancing it in others. Turbulence is not noise, it is structure in motion. On galactic scales, turbulence injected by massive stars helps regulate the overall rate of star formation. Without feedback, galaxies would convert their gas into stars too efficiently, burning through their fuel quickly. Observations show that this does not happen. Star formation is surprisingly inefficient. Massive stars like Behemoth are part of the reason. Their energy output acts as a brake, preventing runaway collapse. In doing so, they help stretch star formation over billions of years rather than millions. This extended timeline is crucial for the long-term evolution of galaxies. There is also a chemical dimension to feedback. As Behemoth sheds mass, it releases material that has been processed in its interior. Even before collapse, its winds carry elements heavier than hydrogen and helium into the surrounding medium. Carbon, nitrogen, oxygen, and other elements appear in the outflows, enriching the gas. This enrichment matters. Stars form from the gas available to them. The chemical composition of that gas influences how stars behave. Metal-rich gas cools more efficiently, it fragments more readily, it forms lower-mass stars more easily. Metal-poor gas behaves differently, favouring more massive stars under certain conditions. Behemoth's feedback therefore alters not only the amount of gas available, but its nature. Over time, this chemical feedback changes the stellar population of a galaxy. Early generations of stars form from pristine gas. Later generations form from enriched material shaped by stars like Behemoth. This progression is written into the spectra of galaxies across cosmic time. Feedback also operates on larger spatial scales. In regions where many massive stars form together, their combined radiation and winds can blow out large bubbles of hot gas. These superbubbles can merge, break through galactic disks and vent material into intergalactic space. This process, sometimes called galactic outflow, removes gas from galaxies entirely. Gas expelled in this way is not lost forever. It may cool, slow, and eventually fall back, but the delay matters. It regulates how fast galaxies grow and how quickly they form new stars. In small galaxies, feedback from massive stars can be especially dramatic. The gravitational pull of a small galaxy is weaker, making it easier for winds and radiation to expel gas. In extreme cases, star formation can be shut down almost entirely for long periods. Behemoth-like stars, if present in such environments, would be transformative. On the scale of large galaxies, feedback shapes structure more subtly. Spiral arms, for example, are sites of active star formation, partly because feedback from previous generations has compressed gas into organised patterns. The bright nebulae seen along spiral arms are glowing reminders of ongoing interaction between stars and gas. Behemoth fits into this picture as an extreme contributor. Its influence extends beyond its immediate neighbourhood. Radiation travels far, winds carry momentum outward, shock waves propagate. The cumulative effect is a redistribution of energy across large volumes of space. There is also an interplay between stellar feedback and gravity on galactic scales. Galaxies are held together by gravity, including the gravity of dark matter halos that extend far beyond visible stars. Feedback injects energy into the baryonic, or normal, matter within these halos. This energy can alter how gas settles into the gravitational potential. In some cases, feedback can flatten gas distributions, change rotation curves, and influence the internal dynamics of galaxies. While dark matter dominates overall structure, stellar feedback shapes the visible details. Behemoth contributes to this shaping through sheer intensity. Another important aspect of cosmic feedback is timing. Massive stars act quickly. They begin influencing their surroundings almost immediately after formation. Lower mass stars, by contrast, contribute little feedback during their long lives. The early phases of star formation in a region are therefore dominated by the most massive stars present. This front-loaded influence sets initial conditions that persist long after the stars themselves are gone. If Behemoth formed early in a cluster, it could have altered the environment so strongly that fewer massive stars formed afterward. Alternatively, it could have triggered secondary bursts of star formation in compressed shells. The sequence matters. Feedback is not just about energy, it is about choreography. The spatial and temporal pattern of stellar influence determines how structures evolve. Dense cores may survive. Diffuse regions may disperse. Filaments may fragment. Cavities may merge. In this way, stars act less like static objects and more like participants in a fluid system. There is also the cumulative effect across cosmic history to consider. In the early universe, conditions favoured the formation of more massive stars. Gas was denser, cooling pathways were different. Feedback from early massive stars would have been intense and widespread. If Behemoth-like stars were more common in those early epochs, their feedback could have played a major role in rionizing the universe, heating intergalactic gas and setting the stage for galaxy formation as we observe it today. Rionization, the process by which the neutral hydrogen filling the early universe became ionized, is thought to be driven largely by massive stars. Their ultraviolet radiation escaped into intergalactic space, transforming the universe's state. Stars like Behemoth would have been powerful contributors. Understanding Behemoth, therefore, is not just about understanding one star. It is about understanding a class of objects that may have shaped the universe at large. There is also a feedback loop between stellar feedback and black hole growth. Massive stars that collapse into black holes seed galactic centres. The feedback they provide before collapse influences how much gas remains available for accretion afterward. In turn, growing black holes produce their own feedback, shaping galaxies further. This layered feedback from stars to black holes and back to galaxies creates a complex web of cause and effect. Behemoth sits at a critical junction in that web. Its winds and radiation shape gas. Its eventual collapse may create a black hole that continues the process on larger scales. The transition from stellar to black hole feedback is not abrupt. It is a continuation. This continuity is one reason astronomers are so interested in extreme stars. They link small-scale physics to large-scale structure. From a human perspective, it is tempting to think of galaxies as vast and stars as small by comparison. In reality, stars are the agents through which galaxies live and change. Without stellar feedback, galaxies would look very different. They might be denser, quieter, and shorter-lived. They might convert their gas into stars too quickly, leaving little room for long-term complexity. Stars like Behemoth prevent that outcome. There is a balance here that echoes the internal balance of the star itself. Just as gravity and radiation struggle inside Behemoth, creation and destruction struggle within galaxies. Feedback ensures that neither side wins completely. If Behemoth reshapes its galaxy, it also invites a deeper question. What else might be hiding beyond our current view? If such extreme stars exist and shape galaxies, are they rare exceptions, or signs of a population we're only beginning to detect? We're no longer forced to work around the universe's obstacles as much as they used to. Instead, they were allowed to look through them. Before this, progress in understanding extreme stars like Behemoth was incremental and cautious. Each advance relied on partial views stitched together from different instruments, different wavelengths, and different assumptions. Results were informative, but fragile. A small change in distance, dust correction, or temperature estimate could ripple through an entire interpretation. Webb altered that balance. The change did not come from a single feature or discovery. It came from the way multiple limitations collapsed at once. Sensitivity, wavelength coverage, resolution, and stability all improved together. When those improvements combined, they did not just refine measurements, they opened regimes that had been functionally inaccessible. To see why that matters, it helps to think about what astronomers were up against. Most of the universe's most interesting processes happen in places that are inconvenient to observe. Star formation occurs inside dense clouds of gas and dust. Massive stars form quickly and violently, often before they can clear their surroundings. The most extreme objects tend to be embedded, distant, and short-lived. Visible light telescopes struggle in these environments. Dust absorbs and scatters optical photons. Even the brightest stars can be partially hidden. Corrections are possible, but they rely on models layered atop models. Each layer adds uncertainty. Webb steps around this problem by operating primarily in infrared. Infrared light passes through dust more easily. It carries information from regions that optical light cannot escape. This alone would have made Webb valuable. What changed everything was the degree to which this capability was paired with precision. Webb does not merely detect infrared light. It measures it with extraordinary sensitivity and spectral detail. It can separate closely spaced wavelengths, resolve fine structures, and do so with stability that allows subtle signals to stand out. This is crucial for massive stars. For objects like Behemoth, small errors in luminosity translate into large errors in mass. If brightness is underestimated by a modest factor, mass estimates can shift dramatically. Infrared observations reduce that risk by capturing more of the star's true energy output. But even that is only part of the story. Webb spectroscopic capabilities allow astronomers to probe stellar atmospheres in detail. Spectral lines reveal temperature, composition, ionization, state, and motion. These parameters are not decorative. They are constraints. When multiple independent constraints agree, models tighten. In earlier eras, a luminous object embedded in dust might be explained away as a cluster of stars or a temporary flare. With Webb, such explanations become harder to sustain. Resolution improves, blending decreases, variability can be tracked. The object either resolves into multiple components, or it does not. Behemoth did not. That persistence is what forced re-evaluation. Another reason Webb changed the conversation lies in its ability to see young stars early. Massive stars evolve quickly. Their most extreme phases may occur while they are still deeply embedded in their birth clouds. Optical telescopes often catch them only after feedback has cleared the surroundings, by which time significant mass loss may have occurred. Webb catches stars closer to their formative peak. This matters because the question of true scale depends on timing. A star observed late in its life may already have shed a large fraction of its mass. Observing it earlier provides a clearer picture of how massive it became, not just how massive it remains. Behemoth's inferred mass benefits from this timing advantage. There is also the issue of environment. Webb does not isolate stars artificially. It observes them within their broader context. Star clusters, gas filaments, shock fronts, and ionized regions appear together in the same data. This contextual information constrains formation scenarios. If a star appears extraordinarily massive but sits in an environment incapable of feeding such growth, skepticism is warranted. If it sits in a dense, gas-rich region with signs of intense accretion, the case strengthens. Behemoth's surroundings support the latter interpretation. This environmental clarity was difficult to achieve before. Separate instruments had to be combined. Spatial resolution varied. Alignments introduced uncertainty. Webb collapses these steps into a single coherent view. There is also a quieter but equally important improvement: calibration. Webb's detectors are designed to operate at extremely stable temperatures. Thermal noise is minimized. Instrumental drift is controlled. This stability allows long exposures and precise comparisons across time. For massive stars, which can vary, this matters. Changes in brightness or spectral features can be tracked confidently, not dismissed as instrumental artifacts. Stability turns snapshots into narratives. Why does all of this amount to a turning point rather than just an improvement? Because astronomy often advances by ruling things out. Before Webb, extreme mass estimates could be dismissed as artifacts of dust, distance, blending, or timing. Each dismissal was reasonable on its own. Together they formed a protective shell around existing theory. Webb punctured several of those escape routes simultaneously. Dust effects diminished, distance estimates improved, blending was reduced, timing moved closer to formation. When all of these factors aligned and the extreme interpretation remained, the burden of proof shifted. Instead of asking whether Behemoth was an illusion, astronomers began asking under what conditions such a star could exist. That is a profound shift. It turned skepticism into curiosity. Another aspect of Webb's impact is its ability to detect populations rather than isolated examples. A single extreme star can always be treated as a fluke. A population cannot. As Webb continues surveying star-forming regions in our galaxy and beyond, it will either find more Behemoth-like objects, or it will not. Either outcome is informative. If more are found, it suggests that earlier instruments systematically undercounted extreme stars. If none are found, it suggests that Behemoth is a rare but real edge case. In both scenarios, the parameter space becomes clearer. Webb also enables comparisons across environments, metal-rich regions, metal-poor regions, dense clusters, sparse associations. By observing massive stars in different contexts, astronomers can test how formation pathways depend on conditions. This matters because theoretical limits are rarely universal. They depend on assumptions about composition, turbulence, and geometry. Webb provides the data needed to test those dependencies. There is also a cosmological dimension. Webb's sensitivity allows it to observe star-forming regions in distant galaxies, looking back in time. The early universe was different. Gas was denser, heavy elements were scarce, conditions favoured different modes of star formation. If Behemoth-like stars were more common in the early universe, Webb is our best tool for finding their descendants or their signatures. Understanding present-day extremes helps interpret ancient light. In this way, Webb links local astrophysics to cosmic history. It is worth noting that Webb did not invalidate previous work. It contextualized it. Earlier telescopes were not wrong. They were limited. Their data shaped models that worked well within accessible regimes. Webb extends those regimes. This extension often reveals that limits once thought sharp are actually fuzzy. Boundaries become bands. Possibilities widen. That does not weaken physics. It refines it. There is a human dimension to this transition that should not be overlooked. Scientific fields develop habits. Certain questions are asked repeatedly. Others are set aside because they seem settled. Webb reopened questions that had been quietly parked. How massive can a star really get? How fast can it form? How long can it persist? How does it end? These questions were never fully answered. They were bracketed by available evidence. Webb expands that evidence. It also changes how young scientists are trained. Data sets are richer. Expectations shift. Models must accommodate a wider range of behaviour. Behemoth in this sense is not just an object of study. It is a stress test. It forces theories to demonstrate flexibility. It forces simulations to incorporate complexity. It forces observers to confront uncertainty honestly. The fact that this stress test emerged from improved observation rather than speculative theory is important. It underscores a central principle of science. Nature leads. Theory follows. Webb has given nature a clearer voice. As this voice continues to speak, it will almost certainly complicate the picture further. Some estimates will be refined downward. Some candidates will be reclassified. New extremes may appear. The point is not that Webb delivers final answers. It delivers better questions. And those questions do not stop at stars. By reshaping our understanding of stellar mass limits, Webb influences how we think about black hole formation, galaxy evolution, and the early universe. Each of these areas depends on assumptions about what stars can do. Change the assumptions, and the downstream consequences ripple outward. Behemoth sits near the beginning of that ripple. The recognition that such a star exists, measured with tools capable of piercing dust and resolving detail, is not an endpoint. It is a recalibration. If Webb revealed Behemoth by looking where we could not before, what other extremes lie just beyond the edge of current surveys? It is difficult to encounter an object like Behemoth without immediately wondering whether it truly represents the edge, or whether it is simply the first clear signal of something larger still waiting in the background. That question does not come from sensationalism. It comes from pattern recognition. In astronomy, whenever observational limits retreat, new extremes tend to appear. This has happened before. The largest planets were found only after detection methods improved. The most distant galaxies appeared only when instruments became sensitive enough to see their faint light. Supermassive black holes were once thought impossible until evidence forced their acceptance. Each time, the universe revealed that our previous limits had been shaped less by nature and more by perception. Behemoth invites the same reconsideration. To ask whether larger stars might exist is not to assume they do. It is to acknowledge that the conditions required to find them have only recently become available. Infrared sensitivity, high resolution, stable long-term observation, and access to deeply embedded regions are all relatively new advantages. For most of modern astronomy, these were missing. That absence matters. The environments capable of forming the most massive stars are precisely the environments that hide them best. Dense molecular clouds, crowded clusters, and distant galaxies all work against detection. Extreme stars form quickly, evolve rapidly, and disrupt their surroundings. They are loud in their effects but fleeting in their visibility. Behemoth may be visible now because it sits at a fortunate intersection of distance, timing, and orientation. It is close enough to resolve, young enough to retain extreme mass, unobscured enough for its light to escape. That combination may be rare. If larger stars exist, they may not be obliging. They could be farther away, buried deeper, or already transitioning toward collapse. Their signatures may be subtle, distributed across wavelengths, or blended with other phenomena. This possibility forces caution in interpreting absence as non-existence. There are theoretical reasons to think larger stars could form under certain conditions. In environments with exceptionally high gas density, accretion rates could overwhelm radiation pressure for brief periods. If gas flows arrive in clumps rather than smoothly, gravity may gain temporary dominance. If rotation and geometry allow radiation to escape preferentially, growth may continue longer than expected. These are not speculative fantasies. They are extensions of known physics into regimes that are difficult to observe. Early cosmic history offers another reason for openness. In the first few 100 million years after the universe formed, conditions were different. Gas was more abundant, heavy elements were scarce, cooling pathways were limited. Simulations suggest that early stars, sometimes called population 3 stars, may have reached masses far exceeding those commonly seen today. These stars would have lived fast and died young, leaving behind black holes and heavy elements that shaped subsequent generations. None of them survive today. Their existence must be inferred indirectly, through chemical signatures and theoretical modelling. Behemoth, while not a primordial star, hints at what may have been common in those early epochs. If modern conditions can still produce stars pushing the upper limits, then early conditions may have allowed even more extreme examples. The absence of direct observation does not negate this possibility. It reflects the difficulty of looking that far back in time with sufficient resolution. Another factor to consider is classification. Astronomers define stars based on how they behave, not just how massive they are. At some point, an object may cease to be recognizable as a star in the traditional sense. Its interior may be dominated by radiation. Its structure may be unstable. Its lifetime may be extraordinarily brief. If such an object forms and collapses rapidly, it may never appear as a discrete star in observations. It might manifest only as an energetic event, a burst of radiation, or the sudden appearance of a black hole. In that case, the question of bigger stars becomes tangled with the question of detectability. It is also possible that Behemoth represents a practical ceiling rather than an absolute one. Nature may allow brief excursions beyond this scale, but not in ways that produce long-lived, observable stars. Objects larger than Behemoth may exist only as transient configurations, never settling into a phase we would classify as stellar. This distinction matters. Astronomy tends to catalogue objects based on stable or semi-stable phases. Stars that exist for only tens of thousands of years may slip between categories. They may be missed not because they are rare, but because they do not linger. Another hiding place lies in distance. Webb can see far, but not infinitely far. Even with its sensitivity, resolving individual stars in distant galaxies is challenging. At large distances, massive stars blend together. Their combined light appears as clusters or unresolved sources. If a star significantly larger than Behemoth exists in a distant galaxy, its light might be diluted by surrounding stars or misinterpreted as a cluster. Without sufficient resolution, distinguishing a single extreme object from many ordinary ones becomes difficult. Future telescopes may address this limitation. Concepts like extremely large ground-based telescopes or next-generation space observatories promise improved resolution and sensitivity. With them, individual massive stars in more distant galaxies may become resolvable. What now appears as an unresolved glow could be revealed as something more specific. The question then becomes not whether larger stars exist, but whether our instruments are ready to identify them. There is also a sociological aspect to this search. Science progresses within frameworks of expectation. When an object exceeds expectations, it attracts scrutiny. Claims are tested, assumptions are questioned, but when expectations adjust, the threshold for surprise shifts. Behemoth changes expectations. What once seemed implausible now feels possible. That does not mean astronomers will lower standards. It means they will widen their search criteria. They will re-examine data that may have been dismissed previously. They will look more carefully at outliers. Hidden extremes often emerge not because new data appears, but because old data is reinterpreted. There is precedent for this. Objects once classified as unusual nebulae were later recognized as supernova remnants. Bright points once thought to be stars were reclassified as quasars when their distances were understood. The universe did not change. Interpretation did. Behemoth may prompt similar re-evaluations. Another reason larger objects might remain hidden lies in variability. Extremely massive stars may be unstable in ways that complicate identification. Their brightness may fluctuate dramatically. Their spectra may change as mass loss exposes different layers. A snapshot observation might capture them in a subdued phase, underestimating their true power. Long-term monitoring is required to understand such objects. Webb's mission lifespan allows for repeated observation, but building a complete picture takes time. Patience is part of the search. It is also possible that Behemoth represents a convergence point rather than a stepping stone. Physics may allow stars to approach this mass range, but not exceed it by much, even briefly. In that case, Behemoth is not the first of many larger discoveries, but the confirmation of a boundary that is broader and more flexible than once thought. This outcome would still be significant. It would mean that stellar mass limits are real but context-dependent. They vary with environment, composition, and formation history. Behemoth would then mark the upper envelope of modern star formation, a benchmark rather than an anomaly. Either interpretation carries weight. If larger stars exist, they challenge formation models further. If they do not, Behemoth helps define the edge with greater clarity. In both cases, knowledge advances. There's also the question of what we mean by bigger. Mass is one metric, radius is another, energy output is a third. Influence on surroundings may be more important than any of these. A star slightly less massive than Behemoth, but with greater rotational energy, or more extreme radiation output could have equal or greater impact. In this sense, size is multidimensional. Future discoveries may not exceed Behemoth in mass, but they may exceed it in other ways. Faster rotation, stronger winds, more dramatic feedback, different internal structures. The universe does not explore extremes along a single axis. This complexity makes the search richer but also more challenging. It requires careful definition of what is being sought. Are astronomers looking for heavier stars, brighter stars, or stars with greater influence? Behemoth sharpens these questions. From a broader perspective, the idea that there might be bigger things hiding is not limited to stars. It extends to every scale of astronomy: galaxies, black holes, cosmic structures. Each time observation improves, the upper end stretches. This pattern does not guarantee endless escalation. It guarantees humility. We tend to mistake the boundaries of our knowledge for the boundaries of reality. Behemoth is a reminder that those two are rarely the same. For now, the evidence supports the existence of at least one star whose scale pushes previous expectations. Whether it stands alone or marks the visible edge of a larger population remains to be seen. Webb will continue to observe. Other instruments will join the effort. Data will accumulate. Some candidates will be confirmed, others will be ruled out. This process will not produce instant answers, and that is appropriate. Astronomy unfolds on long timescales, not just in the universe, but in understanding. Each new capability reveals complexity that takes years to absorb. Behemoth has opened a door, not provided a final view. If stars like Behemoth exist and influence their environment so profoundly, what do they mean for our place in the universe? How does confronting such scale affect the way we understand ourselves, our planet, and our brief moment of awareness? At some point, the challenge stops being technical and becomes cognitive. Not because the data fails, but because the mind reaches a place where familiar tools for understanding no longer scale cleanly. Objects like Behemoth do not merely test telescopes or equations, they test comprehension itself. Human understanding evolved to navigate a narrow slice of reality. Distances measured in steps, times measured in days, forces measured in muscle and momentum. Even when we extend those ideas through mathematics, the underlying intuition remains tied to everyday experience. We can manipulate numbers far beyond our lived scale, but feeling what those numbers mean is another matter. This gap widens dramatically when we confront extremes. Behemoth exists in a regime where words begin to thin out. Massive, luminous, energetic. These terms are accurate, but they flatten nuance. They compress something profoundly unfamiliar into language designed for ordinary things. The result is a kind of intellectual shorthand that works functionally, but not experientially. You can say Behemoth is more than 100 times the mass of the Sun. You can calculate its luminosity. You can model its winds and predict its fate. All of that is legitimate understanding, and yet none of it produces an intuitive grasp of what such a star is like to exist as, even briefly. This is not a failure of intelligence, it is a boundary condition. The human brain excels at pattern recognition within familiar ranges. It struggles when patterns repeat at vastly different scales. 10 meters and 100 meters feel different. 1 million kilometers and 10 million kilometers do not. They blur into abstraction. Astronomy operates almost entirely in that blurred zone. When astronomers talk about Behemoth's core temperature, they may say tens of millions of degrees. That number is meaningful within nuclear physics. It predicts fusion rates and particle behavior. But it does not evoke heat as we know it. It does not map onto sensation. It is an operational value, not a felt one. The same applies to pressure, density, and energy. This creates an interesting dynamic. We can know a great deal about something without ever being able to imagine it properly. Knowledge becomes procedural rather than intuitive. We trust the math, we trust the models, we trust the instruments, We stop expecting to picture the thing itself. That trust is essential. Without it, modern science would stall. But it also introduces humility. Behemoth reminds us that understanding does not always mean internalizing. Sometimes it means accepting that certain realities remain outside direct intuition, accessible only through representation. This is not unique to astronomy. Quantum mechanics operates in a similar space. Subatomic behavior defies everyday logic. We describe it mathematically because mental pictures mislead more than they help. Relativity, too, resists intuition. Time dilation and length contraction make sense on paper long before they feel reasonable. Extreme stars sit at the intersection of these challenges. They involve gravity strong enough to curve space-time measurably, radiation intense enough to push matter away, timescales compressed beyond ordinary narrative, structures shaped by forces that never coexist in daily life. The result is an object that can be studied rigorously and still remain conceptually distant. This distance sometimes leads to misunderstanding outside the scientific community. Headlines simplify. Phrases like "breaking the laws of physics" appear. They are not malicious. They are attempts to bridge the gap between formal understanding and intuitive reaction. In reality, Behemoth does not break laws. It exposes assumptions about smoothness, about symmetry, about steady-state behavior, about universality. Many models rely on simplifications because they must. Complexity is computationally expensive and conceptually messy. Simplifications are not wrong, they are provisional. Behemoth exists in the space those simplifications leave out. This realization can feel unsettling. Humans prefer clean categories. We like boundaries. We like knowing where one regime ends and another begins. Nature rarely obliges. Instead, nature offers gradients. Stars do not suddenly switch from stable to unstable at a fixed mass. They transition through increasingly precarious states. Limits become regions. Boundaries become fuzzy. Understanding this requires a shift in mindset. Instead of asking where the line is, we ask how wide the transition zone might be. Instead of demanding certainty, we work with probability and range. That shift is intellectually demanding. It requires comfort with incomplete answers. It requires patience with ambiguity. It requires the ability to hold multiple plausible interpretations without collapsing into indecision. Science trains for this, but it does not make it easy. Behemoth also highlights another cognitive limitation: scale compression. When confronted with vast differences in scale, the mind tends to normalize them. One extreme begins to resemble another simply because both exceed familiar bounds. A star 100 times the Sun's mass and 1,000 times the Sun's mass may both register as extremely large. Even though the difference between them is enormous in physical consequence, this compression can dull curiosity. If everything beyond a certain point feels equally incomprehensible, the incentive to distinguish diminishes. But in astrophysics, those distinctions matter. Small differences at extreme scales can lead to entirely different outcomes. A slight increase in mass can determine whether a star explodes or collapses silently. A modest change in rotation can alter mass loss dramatically. A subtle difference in composition can shift the entire evolutionary path. Precision matters most where intuition fails most. This is one reason instruments like Webb are so transformative. They do not make the universe easier to imagine, they make it more precisely constrained. They allow scientists to operate confidently even when imagination lags behind. There is also a temporal aspect to this limitation. Human understanding is shaped by narrative. Beginnings, middles, endings. Cause and effect unfolding in sequences we can follow. Stars like Behemoth do not fit neatly into such narratives. Their lives are brief on cosmic timescales, but still unimaginably long in human terms. Millions of years is both a blink and an eternity depending on perspective. Trying to hold that duality strains narrative thinking. We are used to stories with protagonists. Behemoth resists that framing. It is not a character with agency, It is a process, a configuration of matter passing through a phase defined by physics. When we anthropomorphize it, even gently, we risk misunderstanding. Yet narrative is how humans engage. The challenge, then, is to use narrative without mistaking it for explanation, to let story guide attention without replacing mechanism. This balance is delicate. Another limit emerges when confronting consequence. Behemoth's influence extends across light years. Its radiation reshapes gas. Its death may seed black holes or enrich entire regions. The scale of impact dwarfs human affairs. This can provoke two opposing reactions, awe or detachment. Awe can inspire curiosity. Detachment can foster indifference. Both are understandable. When scales diverge too far from lived experience, emotional engagement becomes optional. Science tends to lean into detachment for clarity, but curiosity often depends on a quiet sense of connection. The question becomes how to remain engaged with phenomena that do not include us, do not notice us, and operate on scales that make human concerns negligible. There is no single answer. Some find engagement in the elegance of explanation, others in the challenge of measurement, others in the way such phenomena contextualize existence without diminishing it. Behemoth does not make human life meaningless, it simply removes it from the center. That decentering can be uncomfortable. It can also be clarifying. When we accept that the universe is not arranged for us, curiosity becomes less about self-importance and more about participation. We're not the subject of the universe, we're observers within it. Our understanding grows not because the universe owes us clarity, but because we build tools and frameworks that allow us to ask better questions. Behemoth is one such question made visible. It sits at the edge of what current models can easily explain. It forces refinement without demanding revolution. It invites humility without surrender. There is also a practical boundary worth acknowledging. Even with perfect instruments, some aspects of extreme stars may remain inaccessible. Interiors cannot be observed directly. Early formation phases may be too brief. Collapse events may be obscured. Understanding will always involve inference. This is not unique to astrophysics. Geology infers Earth's interior from seismic waves. Biology infers evolutionary history from genetic patterns. Science often operates by reading traces rather than witnessing causes. The discomfort arises when traces point to regimes that feel alien. Behemoth amplifies that discomfort because it sits so far outside everyday scale while still obeying known physics. It is not a mystery born of ignorance. It is a challenge born of excess mass, excess energy, excess consequence. That kind of challenge does not resolve quickly. Over time, models will improve, observations will accumulate, confidence will grow. What feels unsettling now may become routine. Today's extreme often becomes tomorrow's data point, but the limits of understanding will shift rather than disappear. New edges will appear. This is the pattern science follows. Each expansion of knowledge reveals a larger perimeter of ignorance. Not ignorance as failure, but as opportunity. Behemoth enlarges that perimeter. It reminds us that even as we map the universe with increasing precision, there will always be regimes that strain comprehension. Accepting that is not resignation. It is orientation. As the story continues, that orientation becomes important, because once we recognize the limits of understanding, we can ask a quieter, more reflective question. Not about stars or galaxies, but about meaning. How do objects like Behemoth change the way we think about scale, significance, and place, not as abstractions, but as lived perspectives? Perspective shifts quietly when the question is turned around. Instead of asking how big Behemoth is, or how far it stretches beyond familiar limits, it becomes reasonable to ask whether size itself carries any special importance at all, not to us, but to the universe. From a human point of view, size feels decisive. Bigger things seem more powerful. Larger objects appear more important. We instinctively equate scale with significance because, in our daily lives, scale often determines outcome. A larger animal dominates a smaller one. A larger structure resists damage better than a fragile one. A larger storm causes more disruption. This intuition works well at human scales. It becomes unreliable very quickly beyond them. In the universe, size does not function as a moral category, or even a hierarchical one. There is no sense in which a massive star is more meaningful than a small one, or a large galaxy more purposeful than a faint dwarf. Objects differ in behavior and consequence, not in importance. Behemoth illustrates this distinction clearly. Its size grants it influence. It shapes its environment, injects energy, and alters the chemistry of space around it. These effects are real and measurable, but influence is not the same as priority. The universe does not pause around Behemoth. It does not reorganize itself in recognition of its presence. It simply responds according to physical laws. At the same time, much of what gives the universe its richness does not come from its largest components. Consider the smallest stars. Red dwarfs are the most common stars in the galaxy. Individually, they are dim, quiet, and unremarkable. Collectively, they dominate stellar populations. They burn slowly, persist for trillions of years, and provide stable environments where planets can orbit for unimaginably long spans of time. From the universe's perspective, persistence may matter more than spectacle. Behemoth will live fast and disappear. A red dwarf will still be shining long after massive stars have come and gone, after galaxies have changed shape, after cosmic conditions have shifted. If the universe values anything implicitly, it may be endurance rather than scale. There is also the role of small things in large outcomes. Heavy elements, which play a crucial role in planets and chemistry, are produced through nuclear processes that involve interactions at the level of atomic nuclei. Those nuclei are small beyond ordinary comprehension. Their behavior determines whether stars shine, whether explosions occur, whether matter can form complex structures. Quantum processes inside atoms shape stellar evolution just as surely as gravity does. In that sense, the universe is built from the bottom up as much as from the top down. Large structures emerge from countless small interactions. Size is an emergent property, not a fundamental one. This reframes Behemoth's scale. Rather than being a pinnacle, it becomes a byproduct, a consequence of conditions aligning in a particular way. Dense gas, rapid accretion, favourable geometry and timing combine to produce an extreme star. Remove or alter any one factor, and the outcome changes. The universe does not aim for extremes, it allows them. There is another way to approach the question. If size mattered intrinsically, the universe would likely organise itself differently. We might expect a trend toward ever larger structures dominating completely. Instead, we see balance. Galaxies contain stars of all sizes. Large-scale structure is filamentary and distributed. Matter does not collapse into a single dominant object. Even black holes, the ultimate concentration of mass, do not swallow everything. Their growth is regulated. Feedback limits accretion. Surrounding structures persist. This suggests that the universe does not reward size with unchecked dominance. It permits size within constraints. Those constraints are physical, not preferential. Gravity grows stronger with mass, but so does radiation pressure. Accretion accelerates, but so does instability. Growth triggers counterforces. Balance reasserts itself. Behemoth sits precisely at such a balance point. It is large enough to test limits, but not so large as to override them completely. Its existence does not signal a trend toward ever larger stars. It signals that the range of possibility is broader than previously confirmed. Another angle worth considering is timescale. Large objects tend to be short-lived. Massive stars burn out quickly. Large storms dissipate. Violent events resolve rapidly. Smaller systems often persist. The universe appears to trade intensity for duration. This trade-off suggests that scale is not a simple measure of impact. A brief, intense influence can matter greatly in shaping conditions, but so can a long, steady presence. Which matters more depends on context. Behemoth's influence is dramatic but fleeting. Its radiation reshapes gas quickly. Its death may seed a black hole or disperse heavy elements. These effects are concentrated in time. Smaller stars exert gentler influence over much longer periods. They shape planetary climates, sustain chemistry, and allow complexity to develop slowly. Both modes are necessary for the universe we observe. From this perspective, size is not a ranking system. It is a variable in a larger equation. There is also the question of observation bias. We notice large things because they announce themselves. They are bright, they are energetic, they stand out against background noise. Smaller things often go unnoticed, even if they are more numerous or more enduring. Astronomy, like all observation-based sciences, is shaped by what is easiest to detect. Extreme stars attract attention because they push signals above detection thresholds. That does not mean they dominate reality, it means they dominate our awareness. Behemoth's prominence in discussion reflects this bias. Once awareness adjusts, interest often shifts toward understanding how typical systems behave rather than focusing exclusively on extremes. Extremes test boundaries. Typical cases fill in structure. Both are essential. There is also a philosophical temptation to read intention into scale, to imagine that the universe is building towards something larger, more complex, more powerful. This narrative appears often in popular explanations: bigger galaxies, bigger black holes, bigger stars. Physics does not support this trajectory. The universe expands, but it does not aim. Complexity arises locally, not globally. Large structures form because conditions allow them, not because there is a direction of progress. Behemoth does not represent an apex, it represents a configuration. That distinction matters because it prevents misunderstanding. If Behemoth were seen as an endpoint, its existence would imply a hierarchy. Seeing it as a configuration places it within a continuum. In that continuum, size becomes contextual. In one environment, Behemoth's scale is transformative. In another, it is one influence among many. In the vastness of intergalactic space, its impact fades quickly. The universe is large enough to absorb extremes without disruption. There is also a human-centered version of the question that deserves gentle handling. If size does not matter to the universe, does it matter to us? The answer depends on what is meant by mattering. Behemoth does not care whether it is observed. It does not react to measurement. It does not change behavior based on interpretation. In that sense, nothing we discuss matters to the universe itself, but understanding matters to us. We care about scale because it stretches imagination. It forces re-examination of assumptions. It challenges complacency. Confronting extremes reminds us that reality is not tuned to comfort. This has value. Behemoth matters not because it is large, but because it expands perspective. It exposes blind spots. It encourages humility. It demonstrates that even well-established frameworks have edges. These are intellectual consequences, not cosmic ones. The universe does not reward curiosity. It does not punish ignorance. It simply behaves. Meaning arises on the observer's side of the equation. In that sense, asking whether size matters to the universe may be the wrong framing. A better question might be whether size matters to understanding. Here, the answer is clearly yes. Extremes are where theories are tested. They are where assumptions break. They are where new physics may emerge or where known physics must be applied more carefully. Behemoth matters because it occupies an extreme, but it does not invalidate the small. The universe is built equally from hydrogen atoms and massive stars, from quiet fusion in red dwarfs and explosive collapse in giants, from long persistence and brief intensity. Scale is one parameter among many. As this realization settles, something subtle happens. The urgency to rank or compare fades. Instead, curiosity shifts toward integration. How do these different scales interact? How do extremes and norms coexist? Somewhere between the first question and the last realization, attention naturally slows. After moving through extremes of mass, light, gravity, and scale, the mind does something quiet. It stops trying to hold everything at once, not because curiosity is gone, but because perspective has widened enough that urgency no longer fits. That is often where reflection begins. Behemoth does not sit at the center of the universe. It does not anchor reality or define its purpose. It is one configuration of matter among countless others, briefly assembled under particular conditions, following physical rules without awareness or intent. And yet, the act of noticing it changes something on our side of the equation, not because it is special in a cosmic sense, but because encountering it stretches the boundaries of what feels familiar. Human minds are not built for the vast. They are built for navigation, memory, survival, and story. When faced with scales that exceed those functions, the mind adapts by letting go of precision and leaning into orientation instead. We stop trying to picture everything. We start asking where we are in relation to it. This shift matters. Behemoth is difficult to imagine, not because it is mysterious, but because it is excessive. Excess mass, excess energy, excess consequence. It does not fit comfortably into the mental framework shaped by daily experience. That discomfort is not a flaw. It is a signal that understanding has moved into a new regime, one where certainty becomes less important than coherence. Throughout this exploration, there has been no moment where the universe demanded admiration or insignificance in return. It did not instruct us to feel small or large. Those reactions arise internally, shaped by temperament and interpretation. The cosmos itself remains neutral. Stars do not judge. Galaxies do not compare. Scale has no opinion. What changes is how awareness situates itself. When we encounter something like Behemoth, there is a temptation to collapse into extremes of reaction, awe that feels overwhelming, detachment that feels numbing. Both are understandable responses to scale that dwarfs reference points. Neither response is required. There is another option, quieter and more sustainable. Recognition without dramatization. Behemoth exists. It follows physical laws. It occupies a narrow window of possibility. It will change and disappear. Its influence will persist in altered forms. None of this needs embellishment to be meaningful. Meaning arises from connection, not magnitude. For most of human history, the night sky was a canvas of points. Stars were lights without distances. Size had no clear definition. The universe felt close because it was undefined. As understanding grew, distances expanded. Sizes increased. Structures multiplied. Each advance enlarged the universe conceptually while shrinking humanity's apparent centrality. This progression has sometimes been framed as a loss, as if discovering our lack of cosmic importance diminishes something essential. But that framing assumes importance must be assigned externally. It does not. Meaning does not require central placement. It requires awareness. Behemoth does not care whether it is observed, but observation still matters, because it is how understanding grows. Curiosity is not validated by cosmic acknowledgement. It is validated by coherence, by the quiet satisfaction of seeing how disparate pieces fit together. That satisfaction does not depend on scale. Small discoveries can be as transformative as large ones. A subtle spectral shift can change a model. A refined measurement can overturn an assumption. A better instrument can open entire domains. Behemoth is one such opening. Not because it is the biggest possible star, but because it confirms that the upper edges of possibility are more complex than previously confirmed. It shows that limits are often gradients, that rules often have conditions, that extremes may exist briefly, quietly, without spectacle. This realization is not destabilizing, it is grounding. It reminds us that science is not a quest for finality. It is a process of approximation. Each generation sharpens the picture, knowing that future tools will sharpen it further. There is no final map of the universe waiting to be completed. There is only an ever-improving alignment between models and reality. In that context, Behemoth is not an endpoint. It is a waypoint, a marker indicating how far observation has reached and how much remains unseen. It also illustrates something easy to forget. The universe does not reveal itself all at once. It yields information slowly, reluctantly, often only when conditions align. Technology matters. Patience matters. Interpretation matters. The star existed long before it was noticed. Its properties did not change when instruments improved, only access did. This distinction is important because it keeps attention focused where it belongs. On the relationship between observer and observed, not on imagined hierarchies of importance. Small minds in this sense is not an insult. It is a description of specialization. Human cognition is optimized for narrow bands of scale. We excel at detail within reach. We struggle at extremes. This is not a limitation to overcome. It is a condition to work within. Science extends those limits not by turning minds into cosmic entities, but by building tools that translate vast phenomena into manageable representations, graphs, models, spectra, simulations. Each is a bridge between reality and comprehension. Behemoth crossed one such bridge into awareness. There is also a temporal aspect worth noticing. Stars like Behemoth live and die on timescales that make human history feel momentary. And yet, the act of understanding them unfolds on human timescales. Years of observation, decades of theory, generations of accumulated insight. These two timescales coexist without conflict. The universe does not rush. Neither does understanding when done carefully. That lack of urgency is one of the quiet comforts of astronomy. Nothing demands immediate resolution. Questions can remain open. Uncertainty can persist. Curiosity does not expire. Behemoth does not require a verdict. It invites continued attention. Perhaps future observations will revise its estimated mass downward. Perhaps new candidates will surpass it. Perhaps models will adjust in ways that make its existence feel less surprising. All of those outcomes are acceptable. What matters is not that Behemoth remains exceptional, but that it improves alignment between expectation and reality. There is a subtle emotional recalibration that often follows encounters with scale. Problems that once felt large shrink slightly. Concerns gain context, not because they are trivial, but because perspective has widened. The universe is large enough to hold extremes without collapsing. Human experience is small enough to matter locally without requiring cosmic endorsement. These two facts coexist peacefully. Small minds navigating a vast cosmos is not a contradiction. It is a relationship. We do not need to comprehend everything to participate meaningfully. We do not need to feel large to feel grounded. We do not need answers to every question to rest comfortably within uncertainty. Behemoth does not ask us to understand it fully. It simply exists as an example of what reality can do when conditions align. That is enough. As attention begins to settle, it can return gently to the present moment, to the quiet room, to the steady rhythm of breath, to the simple fact of being awake or drifting toward rest. The universe continues whether or not it is being observed. Behemoth continues its internal negotiations. Light travels outward, matter shifts, time moves forward. There is no need to hold it all. Curiosity can remain open without being active. Understanding can pause without ending. Questions can linger without demanding resolution. This is not a conclusion. It is a resting point. The cosmos remains vast. The mind remains limited. The relationship between them remains ongoing. And somewhere beyond familiar reference points, Behemoth continues to burn, not as a statement, not as a challenge, but as one configuration among many, quietly reminding us that reality is larger than any single frame, and that noticing this does not diminish the observer, but gently situates them within a much wider view that does not close.